everyone, and welcome to the Symposium on Fault Detection, Supervision, and Safety for Technical Processes. So my name is Silvia Carpitella, and I am a professor at the California State University of Northridge. And for me, it's a big pleasure and an honor today to coordinate this session together with Professor Yin Yang from the Western University of Ontario. So the session of today that is focused in safety processes includes 6 presentations, and we are going to begin properly with my presentation. So this work of research that I'm going to discuss with you today has been carried out in cooperation with one of my students, Elena Azevedo, and the work of research is titled Sustainable Supply Chain Control Strategies for the Natural Stone Market. I'm going to just quickly introduce the agenda for the presentation of today just briefly. So after a brief introduction, literature review, and defining the objectives of the study, I'm going to define the approach that was proposed to carry out this study based on the use and the application of multi-criteria decision-making methods. Then after that, I will also discuss and tell you something about a practical case study that we carried out with relation to a practical company, to then eventually conclude the presentation and present future line of potential developments. Yeah, sorry. Okay, sorry. So basically, in order to start with the introduction and objectives, so this paper is focused on the topic of supply chain management. Supply chain management is the process that involves all of the management of the transition of goods from their production to their delivery from the final customers. And so basically, also since I have been working and living in the US, we decided to focus our attention on a case involving international trades between the US, the United States, and a Brazilian company. A Brazilian company from which the United States import natural stones. Of course, like there are various goods that the US imports from many other countries, but the importation of natural stones is very important for carrying out various and several critical construction processes also and projects. Also, of course, apart from Brazil, the states import natural stones from many other countries. And this demonstrates the important role that is played by this kind of international trade. And this is also the reason why we decided to focus our attention properly on this market sector. So basically, in order to improve the process of supply chain management, we decided to focus our attention on the evaluation and management of critical significant supply chain risks. So basically some risks that could involve the process of supply chain management could cause disruptions, and we want to understand how we can actually prioritize and direct actions of management strategies in order to contain these risks and to reduce potentially these risks or even preventing their occurrence. So basically what happened is that we propose a multi-criteria decision-making approaches, because in this process we may have many factors that come into play that we will refer to as criteria. And this slide just briefly reports some of the works of research that have been used to develop our literature review and to actually carry out and conclude our analysis. But what are multi-criteria decision-making methods? Basically, these are frameworks, mathematical frameworks that have been proposed in literature. And the nice thing about multi-criteria decision-making methods is that they are methodologies, techniques based on the use of mathematics, but they can use as input data input coming from experts. So basically they are a fantastic tool, because they can integrate the mathematical validity something that, of course, allows us to achieve sound result at a scientific point of view, but integrating expert experience and the subjective perceptions of experts and stakeholders that actually possess actual knowledge about phenomena. And of course, like we can, since in literature, as you can imagine, they propose a wide plethora of multi-criteria decision-making methods, basically we can choose the method that is more suitable according to the specific type of the decision-making problem that we want to solve. So for example, we may be interested in applying one of these methods when we want to select a single alternative from a wider set of options according to different criteria. Also, we may be interested in applying these methods when we want to rank alternatives, and this is very useful, for example, when we deal with big data, or when, for example, in our case, when we want to produce a prioritization of risks or techniques, or also when we want to draw up, for example, a final list of candidates for a project and so on. Also, these methods are very useful if we are interested in performing clustering operations and inserting alternatives to classes or groups according to their common features. As I was saying, in literature there are several techniques that have been proposed, and of course the choice of the technique depends on the characteristics of the problem and on the objective that we want to achieve, on the result that we want to achieve. The interesting point is also that, as I was saying, they provide mathematical structures, mathematical frameworks by using input coming from human experts. So basically we can integrate these methodologies with mathematical theories, such as, for example, the fuzzy set theory, so that we can also manipulate the data of input and we can manage, reduce the uncertainty affecting and characterizing input data. In this case, in the case of this paper, we propose the application of the TOPSIS methodology in order to achieve a ranking of supply chain risks characterizing the process of supply chain management involving the cooperation between the United States and Brazil in the importation towards the United States of natural stones. And this methodology, we actually chose this specific method because this is very helpful in achieving a final ranking, even of a huge number of alternatives. So even when we are actually dealing with the domain of big data. So this application is not limited to the number of alternatives that basically we have to deal with. And so, in particular, the name TOPSIS is an acronym that actually means Technique for Order of Preference by Similarity to Ideal Solution, because it is grounded upon the concept that the solution to be prioritized will be characterized by the shorter distance to a positive ideal solution and to a farther distance from an ideal negative solution. And at a methodological level, in order to apply to this methodology, it will be necessary to apply several steps and implement several steps in sequence. So, for example, the first step involves the organization of the input matrix. In the input matrix, I will basically collect the evaluations of alternatives under the several criteria that are characteristics of the phenomenon that I am studying. Then, of course, this data will have to be normalized, and also the matrix will have to be weighted, because since we are considering criteria, these criteria, they have not the same weight, they have not the same mutual importance, and their degree of importance depends on the perception provided by, of course, the company and the decision making and the practical actual context. Then the second step consists in identifying the solutions that I was discussing about before, so the positive ideal solution and the negative ideal solution, to then calculate the distance of each of the alternative of my set to these solutions. And then once I calculate this distance, each alternative will be characterized by the so-called closeness coefficient. That is a proximity coefficient that will indicate how performant is basically the alternative that I have at the top of my ranking. And then by ordering these values of closeness coefficient, I will get my final ranking. So basically this is a structured methodology that allows me basically to deal with any type of decision-making methods. And according to my experience, I've been finding that companies love to apply this methodology. And here in this slide, of course, I report some mathematical details, but we can just go straight to the case study that is the most interesting part. So in the case study, basically we focused on a Brazilian company. As I was saying, this Brazilian company is involved in international trades with the US. And this Brazilian company has established its presence in the US over the last 15 years. Basically, they have a warehouse that is located, if I'm not wrong, in the state of Texas, and so they take care of all of the process of importation of the natural stone, exportation, of course, from Brazil towards the United States. And of course, it goes without saying that this process is very complex. So we have many issues that can characterize this transportation process, because it's very important that the slabs, they arrive safely and without being damaged. So basically, the company actually highlighted a set of most critical risks that may happen during this transportation and delivery process. So basically, this represents the stage of the input data collection. So we establish the criteria and their preference directions. And in terms of criteria, of course, we referred to the literature review. So we led an intensive literature review in order to understand which are the most important aspects connected with this type of problem, with similar problems already solved in literature, such as, for example, the impact on delivery time, the probability of occurrence, the severity of occurrence, if actually an actual risk actually occurred, the financial impact that could have the occurrence of that specific risk, and also the difficulty of mitigation of a specific risk. And then it's part of the set of input data, also the alternatives to be ranked. As I was saying, the alternatives to be ranked are the actual supply chain risks characterizing the whole process. And I want to know, actually I want to understand which are the most, the risks that are in need to be managed with a higher level of priority. And so this stage was actually led in cooperation with the company, because of course we led an intense process of brainstorming with the company management in order to understand which actually are their specific needs. And so basically from this brainstorming process, we highlighted several critical points, such as, for example, labor disruptions, limited booking of the material that is in need of being transported, potential delays that may occur at American port. As you can see, there are internal and external, so endogenous and exogenous potential occurrences. And in particular, we highlighted a set of 10 supply chain risks. After highlighting the criteria and alternative, the next step was actually evaluating the impact of these risks under the specific criteria emerged from the literature study. And in this case, also in this case, we actually established a feedback exchange process with the company in order to quantify basically the intensity of each of these supply chain risks. And with the company expert, we used a 5-point scale where the value of 1 represents a minimum impact on criterion, while the value of 5 represents a maximum impact on the specific criterion. And so basically these are the input stage data for the TOPSIS application, but I'm missing something. I'm missing the criteria weights, because of course all of the aspects that we have been previously discussed, they may be perceived as having the same importance by the company, but also there may be some of these aspects that may be more important, that the company want to prioritize the most. So basically, we have been leading an analysis characterized by the formulation of 3 different scenarios. In the first scenario, we considered to attribute the same importance to all of the criteria. So basically, we have 5 criteria, and we attributed a weight of 20% to each of them. In the second scenario, we decided to attribute more importance to the first criterion, that was the criterion of impact on delivery time, while reducing the weights associated to other criteria accordingly. And in the last scenario, we decided to attribute more importance to the last criterion that refers to the difficulty of mitigation. Of course, you can realize that this process is also very subjective because it depends on, once again, on the company needs and on how our stakeholders perceive importance about phenomena. But it's very interesting to have this possibility of simulating different scenarios, also in order to calculate how our solutions are robust. So basically, we led 3 different iterations for the TOPSIS application, and we could find eventually that the solution supply chain risks 3, 2, and 5 occupy the first position. They are at the top of the ranking for the first scenario and the case scenario. But now let's analyze this data. So basically, SC3, so supply chain 3, consists in the supply chain risks of port delays. And supply chain risk 2 will be limited booking and natural disasters. They are actually at the top of the ranking in the case in which I attribute the same importance to all of the criteria, and also in the case in which I attribute more importance to the criterion of impact of delivery time. But in the moment in which I change the scenario and attribute more importance to the criterion of difficulty of mitigation, what happens is that at the top of the ranking, in second position specifically, I find the 10th supply chain risks that refer to the condition of political unrest. That, of course, it's clear that is more difficult to mitigate because it's something that doesn't depend on the company. Also, to conclude the analysis, we basically elaborated a list of potential strategies that will be useful in order to actually manage and reduce the occurrence of these risks. And of course, it's clear that budget is always something that is limited, and so the company cannot implement all of these strategies all at once. So also in this case, we need to prioritize. So our recommendation for the company will be just to start by implementing the strategical actions referring to the reduction of the third supply chain risks, delay at American ports, that actually consistently occupies in all of the scenarios the first position in the ranking. And so, for example, improving supply chain planning, developing alternative shipping routes, establishing strong relationships with supplier and logistic providers, and so on. So basically, in order to conclude our presentation, we have been focusing on this sector, given the importance that at a market level this sector has in terms of exchange between the US and other countries. We have been adopting a multi-criteria decision-making perspective for giving to our analysis, like enlarging the spectrum and to give the possibility to include in our analysis multiple aspects. And also we focused on the case of a Brazilian company that is an actual company engaged in a regular trade with the US in order to provide a method that is capable to say in a structured way how it would be more convenient to lead and organize a process of risk management for the process of supply chain management. And then also we concluded the analysis by proposing a set of practical strategic actions as measures that could be adopted and also on their turn prioritize. Future developments. As future developments, we could also think about, since at this level for this conference contribution, we just engaged a single expert in our analysis. In the future, we may contemplate the possibility of including multiple perspectives so that the analysis could be further and further enriched. And also another possibility could be the integration of other different methodologies for the stage of the weights calculation that could be calculated in a more precise way by applying other methodologies, or by also, as I was mentioning before, integrating other mathematical theories for uncertainty reduction. So I thank you so much for your kind attention, and please, if you have any questions, I will be very happy to discuss.
Thank you very much. thank you for the effective presentation. Just a curiosity, can we consider this tool, since I don't know the tools, the methods, a sort of global sensitivity analysis method? I mean, you analyze the variation of your parameters in a large range, and so you can capture the effect of this kind of interaction in order to obtain the ranking?
Absolutely. So basically the sensitivity analysis is something that can be applied at the end of the method iteration. So basically what I did here was exactly what you were mentioning. So all of these 3 different stages under 3 different scenarios, they are exactly like a sensitivity analysis that has been led on criteria weights. So basically, as you were mentioning, sensitivity analysis is very important in order to understand how our solutions are reliable. Because of course, in the reality, we have a plethora of aspects and factors. So things are not just static, are not just in this way. So it's very important to understand how our results vary when we vary conditions at the borders. So basically, this is the perfect technique and tool to be integrated with sensitivity analysis in order also to understand if at a practical level I am going in the right directions or not. I hope to have answered to your question. Is there any other question?
I think for the interest of time, with sure. One, can you help me? So the next presentation is can we put it on? Okay. Let's put my glasses. Next presentation is aging in process industry. Yeah, identification of material degradation from past accident analysis. You are Morana? Okay, yeah, please. Here is the microphone.
Hello to everyone. I am Morena Vitale from Politecnico of Turin, and I'm going to present our research about aging process in process industry. So the agenda of the presentation is this one. So we'll do a brief introduction of the topic, and I'll explain the motivation of our research. Then I'll explain the methodology for the analysis, the results and conclusion, and at the end, our future steps. So the aging in process plant is a complex system. It's not easy to evaluate the risk of this kind of process. Indeed, it doesn't depend only on the age of the item, but there are a lot of consideration that has to be taken into account as process environment and of course the environment. So in Europe, this is a quite big problem because more or less the half of the plants, of the process plants, were built after the Second World War. So of course, today they're working after the scheduled time. So for this reason, the third SAFEPROCESS in 2012 introduced this problem, but just saying that, that during an inspection, the inspector has to evaluate aging and corrosion, but there are no procedures or guideline at all in this third SAFEPROCESS. And for this reason, it's important to understand how to evaluate this aspect, because it's quite a big problem today. And it's possible to understand how traditional management systems are not enough today. And we are going to see even this part. For a good aging management, it's good to know 3 aspects. The KID. K is knowledge. The knowledge on what can happen on an item in the process plant, and from a chemical and physical point of view. Then the information about the lifetime of the item, And at the end, data. Data about past tests that the industry can done in the lifetime of the item. But the problem is that the KID are useful for a good inspection plan, to schedule the plan, for evaluate the risk, but they are not sufficient for understanding the failure modes. And of course, they are not sufficient for a good inspection. So for this, we try to understand better the failure modes that can happen on an item, how? Trying to analyze past accident. And we did it with the help of a database, for the moment, just ARIA. ARIA is a database built in Europe, in France, actually. But of course, we like to expand our research, and we try to build a repository. This repository structure is this one. As you can see, there is the report number, data, and continent, the country. Then all the other classification are taken from previous research, but of course, we choose the best one for our case. For the cause, we choose corrosion, fatigue, erosion, and vibration, and then we added a label called material degradation that is an unknown type. Then, for the scenario, we divided it into type. A general one that is outcome, that can be accident, incident, depending on the consequences. Then just loss of containment or near miss. So the event could happen, but fortunately it didn't happen. Then a more specific one, the final scenario, that is toxic gas dispersion, environmental contamination, release with no further consequence, fire explosion, and multiple scenario. Then we can see we divided the industrial macro sector for chemical and petrochemical, manufacturing, pipeline, power production, storage and warehouse, transportation, and water treatment. Equipment involved with primary containment system, control and mitigation system, electronic control and instrumentation system, and at the end, structures. Then we choose to analyze even the substance involved with a classification for hazard, so physical, health, environmental, or multiple hazard. And we add even another label called NA, that it means like water, so there is no hazard. And the last one is action taken. Actually, this was done by us, and we choose just 3 labels. As inspection, that means that after the event, the frequency of the inspection were raised, so more inspection. So it's like the inspection weren't sufficient before the event. For inspections already taken, that means the frequency was already high. And at the end, treatments. So after the events, the plant decide to implement new treatments for the material. Okay, at the end, for this part of the analysis, we arrived to 546 reports. And first of all, we have studied the frequency of the reports. The first one it's about 1966 to the 2023. We finished this part of the analysis in the end of 2023, so this number is quite real for the total number of events happened in 2023. I divided this graph in 4 parts. The first one, from 1966 to 1998, we can see how the number of accidents is not so high. It's between 0 and 10, and it's quite constant. But after this year, there is an increase. This can be for the introduction of internet in the industry. So with internet, of course, it was easier to report an accident. So for this, there is this increase. Then I highlighted that 2012, that is the introduction of the third SAFEPROCESS. Of course, this is just the situation in Europe. So for this, I highlighted the SAFEPROCESS. With, as how I said before, the third SAFEPROCESS highlight the importance of this aspect, the aspect of material degradation. And then after this 2012, there is an increase with a peak in 2019. This can be for the COVID, because as we know, in 2020, a lot of plants were not working. So of course, without working, there can happen anything. So maybe this decrease can be for this, and even for between 2016 and 2019, there was the introduction of a quantitative assessment for material degradation, so the introduction of an item, of an index that can help for this, for the evaluation of the material degradation in a plant. Then we can see the deterioration mechanism. The corrosion is the most frequent, so of course we should focus more on corrosion, and then vibration and fatigue. Now we can see more in detail. Okay, for macro sector, we can see first of all how for almost every kind of macro sector, corrosion is the most frequent, but especially for chemical and petrochemical, and this can be for the substance that, that of course are quite aggressive for material. But there are two exceptions, the transportation and power production. The transportation, we can see how in this macro sector, all the mechanisms are quite similar, except from erosion. It's like erosion doesn't affect at all this kind of macro sector, while power production has fatigue as the first mechanism, probably for the process and condition of the process as a different temperature, different pressure that can stress the material. Then another aspect that I highlighted was the second cause of bioprocess, chemical and petrochemical, and manufacturing as vibration. So I wanted to highlight that even vibration can cause a big problem in the process industry. Then the relation between the final scenario and, of course, mechanism degradation. I wanted to start with corrosion. Corrosion as the most final scenario as environmental contamination, probably for two reasons. First of all, for the substance that can cause corrosion are aggressive for material, but even for environment. But that means that this kind of problem are not well managed. While for all the other mechanisms, the first final scenario is the release with no further consequences. That means, of course, that maybe the substance are not a problem for the environment, but maybe in this case, the release is well managed or in a better way. Then we can see how vibration as first mechanism, the first final scenario, the release without consequences. But the second one, is the toxic gas dispersion. This means that there is a strong relation between vibration and toxic gas dispersion, probably for the molecules of the gas that can easily escape from the items. So during an analysis, a risk analysis, this should be taken into consideration. Then the last results that I'm going to present are for the substance. It's possible to see how physical hazards are the most frequent substance, of course, as we expected. But there is a thing that I like to highlight, how 78 events were with the Na substance, so like water, so substance with no hazard. And this means that not only the substance involved has a big role in this material degradation, but there are a lot of aspects that have to be taken into consideration during the risk analysis. Then the action taken, as you can see, this kind of data is not always present on the report, but the most frequent action was inspection. So after the event, they increased the frequency of the inspection. This means that the risk analysis wasn't sufficient, wasn't complete. They underestimated the risk of the material degradation. And similar is with treatment, because if they decide to add new treatment to the material after the event, that means that the treatment wasn't there before the event, the accident. While for inspection already scheduled is just 19 events, but it highlights how even with a high frequency inspection, the event happened. So it's like even the inspection are not conducted in the right way. So this can be only one thing. We need more line guide or procedure for this kind of aspect in the process plant. So our future steps is to expand, first of all, our repository. We'd like to have more data to, of course, conduct a more complete analysis. And we start from NRC, EMARS, and CSB. And then we like, of course, to do again this analysis, so a graphical analysis to understand better the connection between items and the macro sector with the material degradation. But then we like to conduct a modeling phase with event tree and Bayesian network. In this way, we like to predict what can happen in a plant. And especially because we're doing a multi-risk analysis. In this way, we can add even this kind of risk in our analysis. And thank you very much for being here.
Results you showed, they are like a corrosions of very many reports, but you emphasize the ones that is not too many. Why is that?
Because I emphasize the vibration, because vibration are quite different from the others. So, of course, corrosion has a lot of event, so we need to focus more on corrosion, and this is for sure. But vibration is different from the others, so we have to focus on vibration in a different way. For this, I highlighted more this part.
Is someone else has some question? Maybe wants to go before me? No? So just a curiosity. First thing first, thank you very much for the very interesting presentation. I enjoyed it very much. I read in your paper that basically after the pandemic, no, the number of reports in the ARIA database decreased, especially for what concerns the chemical and petrochemical sector. Would you like to build a little bit on this and explain?
Yes. Yeah, that after pandemic there was a decrease in number of reports. But of course there will be a lot of explanation. But in our opinion, is first of all for the pandemic that stopped a lot of process plant, and then there is the introduction of these new index that is quite important because can be a start for us and for, of course, process plant to evaluate this kind of risk. So maybe this can help to prevent in a better way than before this aspect. Yes, yes, of course. We are chemical engineers, so of course we focus even more on this aspect, but we try to study every kind of process plant.
That's great. Thank you so much.
Thank you. I don't know. Thank you.
Thank you very much. Okay, the next presentation is my turn. And my name is Jin Jiang. I'm from University of Western Ontario in Canada. And this presentation is very different from the previous two in the sense that we are looking at a very specific engineering problem. This work was done with my former students, one of my former students, so he could not come here, so that's why I present. The idea is, the title is Adding Smart Functions to industrial-grade transducer or transmitter sometimes for the process for detection and diagnostic without changing the footprint. Right? So that is, let me see, this is, which one is going forward?
This one.
Oh, this one, okay, good.
Yeah.
Okay, good, yeah. So what I want to just give some brief background of this research and look at the objectives. Then we go through what type of smart functions we can add on. But mainly we use FDI or type of algorithms. Then we look at is it possible, and then I'll show you the results, then the validation, and so on. So we all know that you've all seen those type of transmitters in process industry, either for temperature, for pressure, for volume, and some of them even with antennas, laser point. Which one is laser pointer? Is this one, right? Yeah. So some even with antennas, means for wireless transmitters and so on. So the question now is, for this type of transmitters, it has some functions like calibration, changing the range, so on, but it does not have more smart functions such as diagnostics. So our objective is we say, well, we take one, in particular temperature transducer, we look inside, and we say, well, are there any additional resources, computational resources, allow us to add more functions into this transmitter so that you look from outside, it's the same as the transmitter, but it has additional functions. If you look at the transmitter, you say, to decompose it, you have a sensory element. You have a sensory element as the signal comes in. Sensory element, the air conditioning, the conditioning, then it's the readout. So inside, basically, it's we can decompose this sensor, physical environment is temperature, process, whatever. You sense it, then you what we want is, can we add some smart functions such as diagnostics? So that is, if you look at this particular transmitter, they consist of, if you all see the physical system, but if you decompose it, there are many, many layers. So most important things, they are electronics boards. Electronic boards here is, in particular, main processing board. There's a ARM-based MCU, and then we have some data acquisition with A to D, D to A's, and then we have an isolation board. That's everything compacted get together. Then with the displays unit, we form this formula for function. So the question now is, let's take a look of inside. So if you really look at the circuit diagram for these transmitters, you will see that we have main board is over here. Main board, and then we have isolation, this A to D, analog signal comes in, convert to digital, so on. So we look at the computational complexity, or what is available in this main board. Can we implement some of the fault detection diagnostics using the computational resources available to this MCU? It turns out, yes, we can. Yes, we can. So this is very similar to a lot of people talk about edge computing, distributed computing. Basically, this is edge computing. You can do a lot of fault diagnostic at the plant, at distributed side, just using the same sensor. It's already there. We just add the functions. And what we have then we have to perform some analysis for the fault diagnostic, fault detection diagnostic, how much computationally involved. And does MCU provide enough resources to do the calculation? So what we have done is we look at for the main board. They are basically there's communication functions, and also there are some field bus, the profit bus, PA type of stacks is there. And what we want to do is we want to add additional software modules to the system. And so then what we can do is using these modules, we can perform fault diagnostics. So it's very simple, but it's not very straightforward. So we implemented 3 types of fault modules, fault detection techniques. And we estimate execution times about 1 cycle is 160 milliseconds. This is with this process we have is 40 megahertz ARM7 MCU for this particular sensor. So this is how we decompose it. And of course, we work with the company. They provide us with access to their software environment. So we write our program, we download into this module, and we close it down. So this is analyze the total time time constraints for the. We can see that we of course they have communication, bi-directional communication. This is the existing function. We do not want to mess up with theirs. What we have done is we basically just add 2 extra one. One is FDI, one is looking at the prediction type of algorithm. So if we look at the total time takes for task 1.1, so this is the original one, it takes only 13.5% of the CPU power. So there's a lot of resources are lying there, not being used. So when we introduce the FDI, it takes about 17.5% of computational time. And also the predictions is 8.5. So we add them together, we still have quite a lot of computational power is not being used. So in other words, this ARM process, 40 megahertz ARM process is a very powerful process. So what we have done is that we did that, and we have at our lab, we have control system validation platform. So we put this sensor, we install the sensor right there, and then we create some faults in the process. We perform the real evaluation. Of course, we have done the MATLAB simulations and so on, but the idea is that we put this what we call the smart temperature transducer now into the process. Then we have a heater, we have temperature sensors, we have the flow, and so on. I'm show you the evaluation process. What we have done is we did 6 different fault conditions. We said the first one is the heater trip. The heater is no longer working. So no longer working, and then of course temperature will change. And can our sensor detect it? The second is a chiller shutdown. And there's no cooling. The temperature for sure will increase. The third one is a pipe got a plug. This blocked the temperature increase. And this one is for the sensor failure. We lost the signal. Then we look at temperature signal lost for wire is lost. And finally, if we have a leak in the process, the temperature will change. So the results is that, so this is the first one. Heater is tripped, this heating source stopped. We can see that this is quite nicely detect when the temperature changes, when the temperature goes down, it detects the fault. Based on the input-output relation, causal relation, as this morning's plenary talk. And the chiller cooling down, chiller lost, shut down. What we have is that the temperature basically increase. And we can detect that fault as well. The red line is the response for the fault, response of the temperature increase, and this is where the trigger of the fault. So we did a few other things. The chiller shut down. We look at different conditions. Then when the pipe blocked, this fault also we can detect that. So basically, we use this fault detection algorithms right on the system. So we validate those conditions, and it worked. It worked very well. So we summarize some of these results, for each with response time for detection. Detection is time delays. The maximum is 7 seconds, and the minimum is the quickest one is 2 seconds, because it's all depends on how big the fault is, the magnitude of the fault, and so on. But they all seem to work nicely. So our conclusion is it is possible. It's possible to use the existing capacities of the industrial grade transmitters by adding more algorithms, and so that to produce this so-called smart transmitters. The many different definitions of smart transmitters. If you do the Google, you see the smarter, but ours, I think, is smarter because we incorporate some of the FDI techniques into it. The MCU inside those transmitters can accommodate different type of the FDI schemes. So that is quite nice to know. Because we have so much computational power at our disposal, we are not fully utilize it. So you look at the computers, how many computers are basically idling there. If we can do some work, for the benefit of our benefit, that's very good. And so we conclude that this can be a very good way to distribute some smart functionalities to lighten up the load on the data bus within the control system. So what we talk about the fault detection in this conference is can be fault detection diagnostic can be centrally located. We collect the data, we do the fault diagnostics and so on. But we say, well, this will create a lot of traffic, in the plant. If DCS system network, there's a lot of traffic. If you can do it right at the sensor node, then that can increase the overall system reliability and without depending on the porous network. That is basically what I want to talk about today. So if you have questions, more than happy to answer. Thank you. Yeah. Oh, yes, one more.
So thank you for the presentation. I had a question about the faults you were analyzing. Basically, from what I saw, it was either switch on, off, basically to see the impact of that event on your signal readings.
Yes.
So my question would be, did you ever try to consider progressive faults in your system? Because that is where the industry would have the capacity to plan ahead. Otherwise, for such faults, they happen at an instant. So you really can't predict them. So in the diagnostics, yeah, I totally get your point, but for predicting, do you think these edge device sensors do have that capacity to do so?
Yeah, it's a very good point. Continue our discussion from yesterday, this is a very good point. If you want to do the prognosis or look at slowly degraded changes, you need a lot of time to look at the trends. The technique itself, the capacity of the sensor, of course you can do that, but you just need to take more data, take more time, searching for the trend. This particular things, the temperature start increasing. If the pipe is blocked, not completely blocked, it's gradually add up blocking, then you can see the temperature increase. From that trend, you can make decisions. So as far as the functionality of this device, definitely you can do. But the validation scenario we are using, we have not considered for a long time. We have not tried to block it gradually. Maybe that's a very good idea. We should try that.
Yeah, because I think that's where the
Understand.
you can show the capacity, you know, because it's the first thing that you say you do not have that much computation power, right, on
Yes.
your edge device. So
Yes.
that would be like a very good validation
Exactly.
point in a way.
Yeah. The device has this capability, but we have not tried this scenario. Yeah. You're coming from industry perspective. I mean, this is they are most interested to know the degradations. Yeah.
Yeah, true.
Thanks.
Thank you.
Other question for Professor Young?
We can move on.
Okay, so I have just a curiosity again,
Yes.
because I found that very interesting, the fact that you can eventually categorize the different type of failures according to the result of the thermal analysis.
Yes.
And also you were discussing about the possibility of course, selecting beforehand the node where to install the device. So I guess that also other types of parameters that come into play apart from temperature and the device can catch
Yes.
the information.
Yes, the concept can be applied for different types of transmitters. And for our practical implementation, we consider a temperature transducer and with two inputs, the two temperature inputs, so that this one, we can connect a signal from upstream process, the second one from lower part of process. Then we can perform so-called Kalman filters, observers, and so we use parameter estimation-based fault detection. We use autoregressive type of parametric-based this fault detection. But you can input some incorporate different like fast Fourier transform and so on, spectral analysis. This is all possible. That's just different routines you can put it in. So what this work is just to try to prove it is possible. And a lot of people talk about if you say edge computing. This is edge computing. It's not centralized processing. It's you put these functions right in the local level.
Also because I guess that there are some parameters that can be reconnected somehow to temperature studies performed on temperatures, such as vibrations,
Yes.
for example.
Yeah, the
So we can study some.
first step to perform fault detection is to estimate the parameter. Yeah. You're welcome.
Questions for Professor Young? So we can just next paper that is going to be presented is titled "A Modeling Approach of EFT Faults on In-Vehicle Communication Protocols Supported by FTA Analysis."
Daniel, first one. Good morning, everyone. My name is Daniel Porém. I'm from Brazil. It's Rio Grande do Sul Federal University. And we have here our presentation about a modeling approach of EFT faults on in-vehicle communication protocols supported by fault tree analysis. Okay. We'll talk about a quick introduction of informations related works and our motivation. Fault modeling based in no functional restriction and fault tree analysis, case study, fault tree analysis and minimal cuts method and conclusions. In introduction, distributed embedded systems, its growth rapidly in the importation of embedded system is very, very high today. Intervehicular networks applied in communication, use communication for receive information and take care about the important systems embedded vehicle. Okay, safety critical task 2 and transient faults affect definitely the communication. This present research focuses on problems related in performance degradation of regular communication protocols, a kind of EMI, hack attack, etc. This paper presents a study about reliability aspects in embedded communication protocols and modeling of communications faults, applying an example based in electrical fast transient analysis. This study focuses on fault injection, fault tree analysis, aspect-oriented modeling, and non-functional requirements, specifically in early design phases of embedded systems. The design is very important to try allowed these problems in the future in fabrication. Okay. Fault tolerant represents an important requirement for embedded systems that use communication protocols. Recent works highlights the different faults that affect the degrade performance in embedded communication protocols, disrupting signals, generating delays, and avoiding compliance with hard time constraints. Okay. The work report in Hock et al. 2017 presents a concern about the impact of noise for electric-fast transient on CAN network. Identify this fault type can generate deviations in the meantime of communication, the jitter, increase communication delays, latency, and loss of packets, or even damage CAN communications. This work is a part of our research group, and I participate of this work too. Okay. The goal is modeling proactively behavior of fault becomes more and more important today, distributing embedded control systems in order to avoid critical situations to may cause catastrophic problems. We have to remember that many systems embedded vehicles are responsible for critical systems like ABS brakes, ADAS, something like that. If you have a problem with communication, a lost packet, something like that, we can have a big problem, an important problem. Recent experiments performed and Hock et al., Poring, and Santos Rock 2020, 17, 19 e 20, it's a work about our group. It's verifying the performance degradation in communication networks and possibilities of fault modeling in embedded vehicle control systems. Well, this analysis proposal is a test with different values of EFT injections in the communication protocol. Okay, this data was obtained in recent experiments that I said in last slide, is our job, and observed the important specific requirements related to the faults. This is important to observe that our experiments is based in standard IEC 62228 and ISO 26262. Why? There isn't any standard that take care about communication, protocol communication. The standards take care about only about hardware. And this case is the IEC 62228 is take care about CAN FD drivers. But when we make some tests, we have to take some directives, and you take this directive to use for our tests. Okay? This is our workbench created. This is hardware what project developed for these tests. It's about two drivers, two CAN drivers here, and we have AFT injection like this standard said, this standard ask, okay? Here we have a signal that you can see the importation of EFT test with a low voltage peak, we have the deviation of packets. We have the deviation of information. If I improve the value, we have more and more improve of deviation of communication. This proves that CAN is a fact about EFT transients. Okay, well, talking about the analysis of these faults. Test phases with fault injection methods, fault tree analysis according to the full impact analysis, and the fault requirements and specifications is based on RT-FRIDA framework. This framework was developed of our group 2. And this we have the CAN protocol or FlexRay or CAN FD. We have fault injected methods, and we have a different kind of injections, analysis, and you have data mapping. This algorithm, this framework will create a new requirements for industry, for a construction for new equipments to try avoid these problems. Okay? This proposed analysis methodology, process tests and analysis was completed with a fault tree analysis supporting the new process about data mapping on fault impact. The three proposed fault injection, fault analysis with tools, fault tree analysis, then combined to generate an information basis related to fault types and its impact to control system performance. In this work, we emphasize the EFT fault impact, but the methodology can be applied for any fault type that degrade distribute control systems. Okay? Well, the case study is based on a quarter car model. It's a normal based system used to study communications embedded in vehicle. Okay? And this fault tree analysis, we have a basic event, and basic event here, we have a kind of attacks, is electric fast transient, is malicious attacks, and EMI interference, something like that. Okay? But any basic event like this EFT, we have root events. And these events here, it's identified by the value of voltage applied in the workbench. Okay? And this one, it's a way that we can highlight the propagation fault about EFT bursts in CAN protocol. Okay? And we have here the values of propagation and the value of the signals. Here we have an example that the propagation is 0 to 622, and this calculation is about this formula. Each event has a value that's applied about the disturbance in the communication. Okay? Conclusions. Transient faults degrade the performance of distributed controls systems embedded in vehicles. This is a correct sense, it's a concrete. Okay? These transients affect the communication from a simple increase, latency and jitter, until packet loss. The increase, the time between communications, it's a bad situation. And in CAN protocol, normally when we have a packet loss, the way to fix this problem is retransmit. But how many times we will retransmit the information and how many time will take in these retransmissions. This is the problem. Sometimes we have constraint time to accept the information. For example, ABS breaks, okay? In a sequence of fault tree analysis present to show this disturbance in network generate failures. The main issue is possibility to fault modeling in early design phases. The information is based on previous works about EFT injection and performance analysis when the experiment verifies in communication logs registered by tools like a vector CAN analyzer, okay? The present work proposed the integration of fault tree analysis during test phase and requirement specification. Aspect-oriented model and concepts are used to represent a cross-cut impact of faults, providing a better view of fault propagation and distribute systems. So, quick reference. Thank you.
Thank you very much. The question is a very interesting analysis. You look at the fault in a CAN bus system. At the very bottom of your fault tree, you have several different events that lead up to the fault. Have you considered the multiple occurrence of faults?
You can simulate many occurs. This study, I simulate only EFT occurs because our main objective is about EFT.
Yes.
Yeah, and but you can use EMI, for example, you can use simultaneously EFT occurrence at the communication because this kind of noises, it's occur if any situation in bad vehicle. When you switch turn on, turn off, air conditioning, and with switch light, something like that.
So you can. The reason I'm asking this is not just an ordinary question. If you look at the defense industries, the military applications, when the nuclear bomb explodes, okay, and it emits a lot of electromagnetic wave. Mm-hmm. Basically, you have many systems, communication system, computer system, all the system can temporarily interrupt it.
Yeah.
Or even permanent damage, that's including CAN bus.
Yeah.
So there's a lot of research going on. So we started designating a real bomb, but you create a similar thing with very high power, very short, nanoseconds of high pulse to knock down the communication system of enemy communication system. So if your vehicle has CAN bus, tanks, armed personal carriers, this what your analysis will be very important because many events will occur simultaneously.
Yeah, it's the CAN bus. It's the most used protocol in vehicles today. Yeah, but when CAN bus is start to use in vehicles, we have a little equipment embedded in vehicles. Today we have more and more systems embedded. Yeah. When CAN bus start to use, we almost have 15 ECUs embedded vehicles. Today we have 150 ECUs embedded in vehicles. And we have more and more packets of communication, and important packet of communications goes through CAN bus. But it's not the problem. CAN bus manage these packets, but it's not prepared to avoid this kind of problem. Okay. This is a problem. This is the original of our study, our insights.
Any other questions?
Any other questions before me, just in case? No, yeah, so basically, with relation to what Professor Young was saying, of course, in the case in which you start to take into account the occurrence of multiple scenarios, is also very important, I guess, considering some type of dependability analysis to understand what trigger what and vice versa. And building on this, I read in your paper that basically for future developments, you aim to practically apply this procedure to a real case context. So my question and my curiosity was if you have already defined, for example, the borders of the analysis, the specific system that you want to analyze, for example, which type of vehicle it is, because I guess that the real context also will likely influence what will be the final results. Thank you.
Yeah, if you look here in this picture, here we have an edge computer connected at that board to understand and to make some reports about use AI to identify this kind of noises, EFT, something like that in communications. Our job, our work at that time, it's working with edge computing, and here we have two MCUs, ST-MCUs that use edge intelligent artificial embedded to identify this noise, this injection, this work of this one. Yeah. Thank you. Thank you so much. Thank you.
The next presentation is going to be given by video. It's entitled Short-Term Photovoltaic Power Forecasting Based on Kernel Range.
Good morning, everyone. Today I am going to talk.
Okay, we can start.
Good morning, everyone. Today I am going to talk about an exciting topic in renewable energy entitled Short-Term Photovoltaic Power Forecasting using kernel ridge regression. This presentation will cover the basic of photovoltaic power forecasting, introduce kernel ridge regression, and explain how it can be applied to improve the accuracy of our prediction. In this presentation, we will cover several important parts of our research, starting by the introduction, moving to explain the proposed methods. After that, we will present and discuss our results, and finally, the conclusion and perspectives. Let's begin by the introduction, where the renewable energy source, especially solar energy, have gaining significant traction globally due to their potential to provide sustainable, friendly energy future. Also, the renewable energy offers sustainable alternative to conventional power source. However, it must be recognized that exploring new clean energy source is only one aspect of reducing the impact of energy consumption. By adopting effective energy management strategy for optimizing energy source production, distribution, and use, where the energy management is a deliberate method of dealing with the constraints and issues that come with energy consumption. It ensures sustainability, stability, and efficiency in complex energy system. It is pivotal in limiting energy consumption and ensuring the efficient use of energy resource. Energy management encompasses various processes, of which forecasting and optimization play significant roles in this work. We have working on the forecasting parts where the primary aim of energy forecasting is to improve the reliability, sustainability and cost effectiveness of energy production. Let us take a tour through the various temporal dimensions of forecasting, learning about the numerous intricacies that distinguish very short term, medium term and long term. It is crucial to note that scholars frequently disagree on the precise definition of forecasting horizon. The following figure highlights the difference between these horizons and their use in the electrical business. For example, the very short term with a time frame spanning from minutes to hour ahead. The very short-term forecasting play pivotal roles in various applications. It enables the prediction of short-term fluctuations in electricity prices, facilitating the optimization of consumption and cost management, and so on. So, how can we improve photovoltaic power forecasting? One effective approach is using the kernel ridge regression methods, which I will explain it in the next slides. So I will explain our proposed kernel ridge regression methods in 4 parts. The first part is the kernel. So I will explain our proposed kernel ridge regression methods in 4 parts. The first part, which is the kernel trick, where the carrier operates in a high-dimensional feature space in implicitly mapping input features to a higher dimensional space using a kernel function. For the second part, which is the training process, the carrier learns the optimal weight for each feature where the kernel matrix is computed based on the chosen kernel function. The techniques like gradient descent or closed form solution are used to minimize the regularized loss function. Moving to the objective of these methods, where the objective is to minimize the difference between predicted and actual target values while controlling model complexity and preventing overfitting. The regularization parameter, often denoted as alpha, determines the trade-off between fitting the data and avoiding overfitting. Finally, the prediction process, which is used to make predictions for new data points. The carrier here computes the weighted sum of kernel evaluation between the new points and the training data. The regularization term ensures that the model generalizes well to unseen data. Now, let's take a look at the simulation results. The stand-alone or off-grid PV system is considered in this study, where the PV system is independent of the utility grid. We have studied this type of system by supplying with a load based on the climatic for the purpose of extracting the power. The following figure displays the equivalent circuit of a PV cell. So in this analysis, KC PV module is taken into consideration. Moving now to describe the dataset, where the collection of data inputs was employed in this experiment. As data or each data sample in this set has been split into two subsets, one to train the network and the other to test the overall performance of the training network. The results of forecasting are obtained through the toolbox of MATLAB. The data were occurred in Goodwin Creek during daily hours with 1 minute solar interval in order to implement the suggested model. These records corresponded to the days from 1 July to 9 July 2017. In fact, we fed the studied system with the origins and the temperature, which are done in the database detailed above to extract the power. This figure shows us the curve of the temperature, irradiance, and the power at once measured on one day. This figure shows us the variation in irradiance is rather minor compared to the variation in power, and the temperature variation is mild. This leads to the conclusion that when temperature is not a relevant factor, irradiance has a large influence on power. In our experiment, we utilized various data sources, especially to determine the power output of the system under examination. We employed irradiance and temperature data obtained from the comprehensive database described earlier. This process involved estimating the power output for energy for every possible pairing of irradiance and temperature values. Moving now to present various metrics used to assess the carrier performance. We have the mean error, which measures the average prediction error. We have the mean absolute error, absolute difference between predicted and actual values. We have the root mean square error, standard deviation of prediction errors. And finally, the coefficient of determination, which indicates the proportion of variance explained by the model. The following table presents our results using the criteria described in the previous slide. Our empirical studies showed that the kernel ridge regression method is highly effective for short photovoltaic power forecasting. The method demonstrated low error rates, indicating its usefulness in this context. In the chosen scenario, it is worth noting that the kernel ridge regression approach performs admirably across multiple criteria: the mean error, the root mean squared error, the mean absolute error, and the coefficient of determination are recorded as 0.44, 20.59, 60.90, and 1.0 respectively. We can see in the same table that the predicted power have almost the same predicted values of the irradiance, especially for the mean error and the coefficient of determination, where it achieves 0.45, 34.15, 24.92 and 1 respectively for the mean error, the root mean squared error, the mean absolute error and the coefficient of determination. The two predicted variables have a perfect fit according to the coefficient of determination. The following figure depicts the predicted radiance and power for the proposed cases. The results show that the mistakes are significantly smaller, demonstrating a great predictive performance for this scenario. As a result, this particular set for examples demonstrates a noteworthy level of forecast accuracy. Moving now to the final step in this work, which is the conclusion and perspective. In this study, this study demonstrates the effectiveness of the kernel ridge regression methods for short photovoltaic power forecasting. Also, the low error rates suggest that this method would be a valuable tool for energy management in the context of renewable energy. In perspective, our future research could explore other artificial intelligence methods and optimize their parameters to enhance the performance. Thanks for your attention, and I am happy to take any question you may have.
Of course, you are welcome to direct any question you may have to the speaker by contacting via email. And the next and last presentation is going to be online as well, and it's going to be titled Sensors Fault Detection and Diagnosis, Methods and Challenges.
Just before we start the next one, are there any comments on the previous presentation? Questions we can ask her for the discussions?
Everyone.
Pardon? Yeah, I have some comments. You have some comments for previous one, yeah? Sure. So we can have a discussion.
Of course.
I saw the simulation results. Actually, it's covered a time frame, I think it's 2,000 seconds, but that's not correct. For daily profile as a solar PV should be 24 hours. So 24 hours. No, it's second. It's second. I saw it's second. So that's why I get confused.
We have time, so.
Yeah.
That's
Which is the conclusion and rather minor compared to the variation
go to
in
next
power.
one. Next one. Next. 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 Yes.
Oh, okay.
You see here. It's second, right? The S means second.
Yeah.
So maybe there's a typo. Maybe it's a minute. So, but they put as second.
Okay.
So if it's, let's say, so for 1 day, it's minutes, I think it makes sense. It's around 1,000 minutes for 1 day.
But it seems to me she probably found truncate with the middle.
So 1 day, 24 hours, like 30 minutes. Yes, yes, it should be minutes. It's a typo. Yeah. It's not seconds. Typo. Okay. I get it.
Thank you so much for catching that. I think it would be very nice, maybe like if you could also contact the speaker, maybe like you can have a further discussion.
Right? For 2 days. For 2 days provide.
2 days.
And also you see, even during the long peak time, actually there's fluctuations there. So I want to know why the fluctuation happens. That means after sunset sometime,
there's a power generation from the solar panel. But even in early morning there's a little bit power generation still. So this from where? So this, where's this also from?
Where is it also from? From Italy, right? She's Italian, is she?
From Italy? Or
I
from?
don't think so. Doesn't look like an Italian name, so.
Yeah, because for the profile, actually for every place is unique. Because for here, the peak, the shape, it's not like, you see there's a lot of oscillations in the first day, probably it's a cloudy day, maybe it's a rainy day, but the second day is very clear. That means there's a lot of reapers there, means maybe it's a good weather day. But I'm interested to see this profile, what it is. I need to know it. I want to know more about the geography information. But anyway, it's interesting. Thank you.
No, I mean, even virtually, I please encourage you to be in touch with the author and discuss this issue further. So thank you very much for catching this.
So if not, we'll move to the next one. Right? Look at the sensor fault detection.
Everyone, I'm Yu Zhang from SAFEPROCESS University. Today, I will be presenting on the topic sensor fault detection and diagnosis, methods and challenge. This work is a collaboration between the University of Hertfordshire, SAFEPROCESS University and Nanjing University of Aeronautics and Astronautics. I will introduce this topic from the following 5 parts. Provide a means of detecting the actual operating condition of a machine at any point in time. They play a crucial role in ensuring that machines operate efficiently and safely. However, despite being engineered to withstand various conditions, sensors are not immune to faults. Prolonged use and environmental factors often contribute to sensor faults. These faults can stem from aging, wear and tear, physical damage, or issues related to electromagnetic interference and electrical disruptions. As sensors age, their performance can degrade, leading to inaccurate readings. These faults can significantly impact a machine's control system. When a sensor fails or provides erroneous data, it can lead to reduced performance of the machine, generate false warnings, or in service cases cause emergency shutdown. This highlights the importance of effective sensor fault detection and diagnosis. Dissidents like the aborted space shuttle launches such as Challenger, Discover, and Columbia, attributed to sensor failures, serve as stark examples of the critical importance of reliable sensor systems. Sensor faults come in different variants. Some selected examples are listed below. Look at the picture. They are drift sensor faults, hard-over sensor fault, erratic sensor fault, spark sensor fault, and stuck sensor fault. In general, the methods for sensor fault detection and diagnostics can be divided into the following 3 kinds. The first type is model-based techniques, which includes observer-based method, party space method, parameter estimation method. The second type is signal processing based technique, and the last type is the data-driven techniques. After reviewing the sensor fault FDD method, We also list some challenges and future work directions. The first one is how to distinguish sensor faults from machine faults. As we know that the most significant challenge in sensor FDD lies in accurately discerning between anomalies detected in sensor data from genuine faults in machine components. If we want to address this challenge, we also listed some promising study methods. The first one is to implement a redundant sensor system for cross-validation. And the second promising method is to analyze unique fault signature and integrating contextual information, which aid in distinguishing abnormal sensor readings from real mechanical issues. And the last one method is to use machine learning algorithm theorem for pattern recognition, which will engage domain experts for interpretation. Is about scalability and generalizability problem. Scaling sensor FDD system to accommodate various sensor type, models, and operating conditions poses a significant challenge. Creating systems that are not only effective across diverse sensors but also adaptable to different industrial or operational environments requires robust and generalizable methodologies. To address this challenge, we can implement standard interfaces and modular architectures allows seamless integration of diverse sensors. While transfer learning and future extraction technologies leverage shared knowledge across sensor types for robust algorithm design. The third challenge is from the data quality and pre-processing. The quality of sensor data significantly influences the accuracy and reliability of fault detection systems. Challenges arise from dealing with noisy, incomplete, or inconsistent data. Effective processing techniques and data cleansing methodologies are necessary to handle these issues and ensuring the reliability of fault detection algorithm. To address this challenge, the effective processing techniques such as filtering for noise reduction, imputation for missing data, and outlier detection enhances data reliability. Also, developing adaptive processing techniques that dynamically adjust to varying data patterns further enhance fault detection accuracy in real-time scenarios. The fourth challenge is about explainability and interpretability. Interpreting and explaining the decisions made by sensor fault detection and diagnosis algorithms is critical for acceptance and trust in industrial setting. To address this challenge, we can adopt a strategy to make the decision-making process transparent, particularly when using black box artificial neural network methods. Also, the techniques involving model agnostic explanation like SAFEP and LRME, alongside simplified or rule-based models, offer insights into how input features impact predictions. Is to handling latent and unknown faults in real-time sensor FDD. Real-time sensor FDD plays a pivotal role in answering fault tolerance, especially in autonomous vehicles, drones, and safety-critical systems. The foremost challenge lies in managing latency effectively, reducing the delay between event detection and decision-making, while also addressing unknown sensor faults. Addressing this challenge can involve leveraging edge computing for real-time data analysis and developing adaptive algorithms employing anomaly detection and continuous learning mechanisms enable the system to identify unforeseen faults and dynamically adjust. The last challenge is about adapting for resource-constrained edge devices. Using edge devices for deploying data-driven or machine learning methods offers a promising avenue to address latency concerns by processing data closer to the source. Nevertheless, the limitation posed by edge devices such as restricted memory, processing power, and energy usage remain a significant challenge. To address this challenge, we can develop strategies that optimize computational efficiency while maintaining accuracy, such as lightweight algorithms or compressed models. Utilizing collaborative edge cloud architectures for offloading intensive computations and employing energy-efficient computing methods to reduce power consumption. I'd like to conclude this work. As modern industrial and physical systems evolve to enhance their reliability, sensor faults emerge as a critical challenge, posing a potential weak link in integrated health management. There is a growing focus on research aimed at comprehending various sensor faults to enhance the effectiveness of sensor fault detection and diagnosis. This presentation delves into the advancements in sensor fault diagnosis methodologies, outlines prevalent challenges, and identifies promising avenues for further research in the implementation of sensor FDD system. Okay, that's all. Thanks for listening. If you have any question, you can contact me with the email.
Okay, just like the last presentation, any discussions, any comments?
Any comments or remarks? Professor Young, would you like to say something about the presentation? From the audience? So I think that we can conclude the session. My personal thanks for attending the session. Thank you, Professor Young, for co-chairing the session on process safety. I guess that we have been hearing a lot of interesting research this morning. So just from my side, I wish you a very good continuation of the conference and of the day.
Yeah, thank you very much for coming. You know, this weather is so nice outside, but you decide to stay here with us. Thank you so much. So I declare the session is closed, finished. Thank you. Yeah.
first one is on the effect of graph complexity in an energy-based FDI approach. And with this presentation, this paper will be presented by Smith John Hendrick. Please.
How's the sound? Not too good. Okay, so as you can see, my name is Jan Hendrik Smith, or JH. I'm actually glad to see a few people here. I was worried that after the lunch, everybody will disappear. Anyway, so for today, I'd like to elaborate a little bit on my research with regards to graph complexity, especially within the energy graph-based visualization technique. So just as an outline, what I want to do is just give you a quick introduction overview. Then we'll go to the research question as to specifically what we want to address with this paper. I'll look at the energy graph-based visualization technique, just a quick overview as to how it works. Then we'll continue with graph composition, which is actually more the research that I'm focusing on currently. Then I'll discuss a small case study with the Teresa system, the comparison of results and discussion there, and finally I'll conclude the session. This thing works nice. So as we all know, modern industrial systems tends to become more and more complex. And with this complexity, it introduces some challenges with dimensionality in general. And then also, parallel to this, the increased requirement for safe operation becomes more and more of an issue or a challenge. And with that, we need systems that can run reliable. So the energy graph-based detection, what we are focusing on is something that we see that's becoming more and more relevant. Literature shows that using energy and using graphs in fault detection methods is something that seems to be feasible and therefore takes some attention from the academic community. So with this, when you apply graph-based FTI techniques, the graphs tend to take the complexity in the industrial system in terms of the dimensionality and have similar challenges. So your graphs become big or large graphs with the same dimensional issues that we see in the large complex industrial systems as well. So if we look at the literature, those type of dimensional issues is typically addressed within the fields such as machine learning, statistical process control, and so on, as well as with this energy graph-based visualization method that we are focusing on. There's a few sources. If you want more, obviously everything is within the paper as well. So, like I said, we'll be focusing mostly on the energy graph-based visualization method. So to give you a little bit of an overview as to how this works, basically, oh, sorry, before we get to that. So the research question was then, if we look at graphs in general, how does the graph cardinality in this graph-based visualization method affect the performance of the system? So if I use this technique and I go on using it for fault detection, how does the size of the graph actually affect the ability to do fault detection and so forth? And this led to a bit more specific questions, like what is the relationship between the graph cardinality, and in the method we use singular values or eigenvalues for the final analysis. So what's the relationship between the size of the graph and the final singular values that we analyze? Then more specific also, what is the extent of the graph, or to what extent can the graph be reduced without losing too much information that's required for the end fault analysis? And then finally, can the fault information from reduced graphs be observed in non-reductive parts? So if I have a large graph that represents some system, and let's say component or node 1 represents component X, and component X is now a component that I don't include in my graph, so I neglect that node, can I still find faults within that specific node that's propagated through the rest of the system? So to give you a quick overview of how the system works, I won't be going into too much depth, especially since one of my colleagues discussed this yesterday as well. But just as a quick overview, we'll typically have some system that can be represented by a PNID diagram, and we are typically able to construct some type of directed graph for this. Now, in our case, we specifically look at node and link attribute, which is in the energy domain. So for the nodes, typically we'll use something like the rate of change in exergy, whereas the interactions between the components, which is your links. So, sorry, the interactions between the components like that or this is typically considered to have a link attribute, which is just the rate of change in energy exchange between the two. Then we can define a formal graph as the ordered pair G, such that we have node and links with your link and node attribute as this. We can then represent this whole graph as some node signature matrix, which is defined in this manner, which means for the previous example, the previous graph, this one over here, I can construct a node signature matrix that looks something like this. So I have my node attributes over here, and each of the rows is my link attributes. And then, well, I won't be going into too much depth here, but since these parameters encapsulate some of my structural information as well as the causal information in the graph or in the system, it tends to argue that when you have this in an online system, you'll have, for each of the measurements that you take in the system, a matrix that's composed of a bunch of energy attributes like this. And then those can be compared in various ways in order to get some residual or some cost matrix. For our application, we typically use this formula, which is the heterogeneous overlap Euclidean metric, bit modified for specific applications that we've been using it. We'll then typically analyze those matrices, which is, by the way, a square matrix, and we'll look at things like the singular values or vectors, or we can look at the eigenvalues, eigenvectors. There's actually two other methods that I'm not discussing in this article as well. For the last 2 or so years, it became more prevalent to use the eigenvalues or singular value approach. Both of them seem to work a little bit better than the other earlier approaches that we've been using. From this, then, we can construct some type of fault signature, and those fault signatures can either be quantitative in nature or qualitative, depending on what we want to do with it. So, like I said, my focus is more on the construction of the graph itself. So in order to do that, especially in more complex systems, there's a few things that we need to take into account. Typically, what we do, just as a general process, is we start by obtaining obvious information of the system itself. And there's a bunch of things that goes in there, because you can have expert information, or you can just rely on the system performance itself, or a combination of all of those. I'm actually busy writing a follow-up article that hopefully will see the market soon, that discusses this first part in more detail. We'll then generate nodes and links, and we'll assess the validity of this nodes and links. And a lot of thought goes into what should happen here, because depending on how you construct your graph, it influences what happens later on in the system. Now, this discussion will focus exactly on to what extent does that influence the performance. Then we'll remove some of the invalid and redundant links. So typically, if you have a large system and you can't get certain data and it's not able to, or you're not able to model aspects of the system to get that data, then obviously those links is just redundant, or those nodes are just redundant, and you'll have to neglect it, which is where this specific part comes in. So once we're done doing that, we can ask if all of the information that we require in the nodes or the links is available. And if it's not, we can repeat this loop until we get to a point where you have a graph that represents something workable. And if everything checks out, we generate the node signature graph, and that's basically the end of this process. So if you look at some of the guidelines that we've been using up until this point, there's basically 7 of them. The first is that we typically look to include components in the system as nodes if we want to get faults in that specific node. So if there's a compressor in the system and we expect that there might be faults in that and we want to analyze it, we'll include that as a node. This was one of the criteria points that we've been using up until this point. That is not necessarily something that we'll have to do. And you'll see at the end of this discussion why I'm saying that. Secondly, we'll select components where there is energy conversion happening. So for example, if you look at a large system, you need to ask the question as to what of these aspects in the system is actually a component and which of them might be seen as just a subcomponent of the large system. So something like a screw or a nut can still be a component in the system, but it's not applicable to what we've been doing. And that's why we include this specific point. Thirdly, selecting components which require the attribute. Yeah, of course. If we can't obtain the data, then we can't include that as a note. And this is both in terms of the practical aspects. So there's a sensor there, and we can get the data from the sensor, as well as can we model it if that specific part is not included. Fourthly, which of the components have a bunch of energy inflows? So if I have a tank in the system with 20 inflows, that might be a good idea to include that tank as an accumulator node in the system, rather than looking at one of the subcomponents that maybe have an input and an output, especially when I want to reduce the complexity of my graph itself. Fifthly, we select components that will affect the system. So if there's a small change in the energy, we will ask to what extent will this small change affect the whole system process. Therefore, if small or relative small energy flows is through that specific component, it might be a good idea to say, let's neglect this specific component, rather include something else as the node in order to reduce the complexity. Then fourthly, we select components where there is large amounts of energy inflow. Firstly, there's the connectivity aspect, that is 0.4. And then secondly, there's the size of the connectivity. So if it's an energy inflow with a small number, then that might be something that we can neglect. Or if it's a larger number, the prevalence if something happens there, or the effect of that might be bigger, therefore we include that as a note. And then lastly, we can neglect nodes that do not influence the system operation and are not required in guideline 1. So in some cases, you'll get a component where that specific component tells me something about what happens in the system. It's maybe part of a redundant control system, or for example, the system have different modes. So let's say it's a battery that's being charged and discharged. In the charging mode, this node can be active, but in the discharge mode, it's maybe not active. So I might neglect that as a node. So if we look at the case study, this is a plant that runs in Germany, Zittau, at the Hochschule there. It's a thermal process plant specifically designed for research applications, where they have a heat circuit that can either be steam or hot water, and they use it to charge an accumulator, basically a geyser, which is that part over there. And then this acts as if it's a steam or heat battery. And this can be connected to a bunch of smaller systems that they typically want to test. So if you have some steam engine or some heat process that requires steam, they connect it to the system and they can do a bunch of tests from there. So it's perfectly situated for the type of research that we've been doing, where you need a bunch of reliable data and maybe be able to connect a system that has a fault in order to get reliable fault-related data, even though you know that the system itself is, or the larger part of the system is running normally. So for this, we can construct a PNID that looks more or less like this. I've neglected or taken out a bunch of the smaller components like the valves and support aspects. So if you quickly run through that, we have the preheaters on the start. So typically at this point, my atmospheric fluid will come in, so something like water at atmospheric conditions. It will go through an ionizer, and then there's two preheat circuits. Either one or both of them can be utilized at once. It then goes through the boiler itself or the steam generator, and if required, we can then superheat the water to a higher value steam as well, or higher pressure and temperature steam. Then finally, it goes into the thermal battery. As I said, this thermal battery can either be charged with steam or with hot water. And then we have our heat sink or tank accumulator. This is actually a single unit. So inside this compartment here, this part represents that small tank over there, and the other part over there represents this one here. And this also introduced some challenges as to how you construct the graph itself, because in principle, there's some energy exchange in between these two tanks that I can't measure. I don't have a sensor in there that says how many of, or how much of the energy in this part is being transferred to the other part. So considering this as two units or two separate nodes might become a little bit difficult. So it might be a good idea rather to include this as a single node. And then finally, we have our cooling circuit or heat exchangers on the side that then just takes out the excess heat to a facility next door to this specific one. So if we look at the system itself, what we have is basically 5 modes. So like I said, we have a warm-up part where the system starts from atmospheric conditions being warmed up. Okay. And then the other parts as well. So I can construct graphs for each of these systems. So a complete graph would look something like this. If I look just at the charging mode, then it might be something like that. And if I look at the discharge, it might be something like that. So a bunch of the nodes is being neglected because when it's in that specific mode, those components is not active in the system. So there's 2 approaches. One can say I'm looking at this graph and in the node signature, there's just a bunch of zeros. Or I can neglect some of the nodes in addition or at the beginning, resulting in something like that. And then my node signature matrix is smaller, reducing the computational complexity for the mathematical analysis. In the practical sense, we did have 5 data sets. Those 3 were under normal conditions, and these 2 had some faulty aspects in it as well. So when we did the whole analysis, if we plot the singular values, then basically what we got for the full graph, your graph on the charging conditions and your graph on the discharging conditions are these scenarios. This is specifically for data set 89, so the normal conditions. And then if we look at the 2 faulty conditions, we have something like this. Now, important to notice this specific graphs, these 4, that's this first singular value, this is the second singular value. This was starting at a system that was shut down, being warmed up, all the way through, going, charging, everything back to discharge at the end. Whereas this data only zoomed in at a part where the system was charging. So you can see that, look at this as a subset of the process that happened in this system as well. Now, interestingly, if we look at the graphs itself, there's a few observations. So firstly, the singular value patterns stay similar regardless of the graph complexity. So we can see, for example, that there's some changes that we see there, and there's similar changes there. It might be more prevalent in this one. So there's similar patterns regardless of the fact that this graph is quite smaller than the one at the top, and the same for the one at the bottom. But we do see that there is some resolution loss. This is especially clear there when the graphs become really small. I think this is as obvious as expected. Then the pattern changes can be observed regardless of the graph cardinality. For example, we still have this spikes regardless of how large the graph was. Then the SVD plot, and I'm not sure why this happened yet, it seems to be inverse for SVD 1 and 2. For example, there's a part that goes up, and it looks like it's going down for the second SVD. Maybe someone has a clue as to why this is happening. And then finally, the singular value plot have a relative size equal to the number of nodes. So if I look at that one, there was about 20 nodes in the graph, and we get a singular value that's around 20 as well. That's specifically for the first singular value. It doesn't hold for the second, and so on. Lastly, it seems like the lower cardinality graphs have less noise, which is, well, maybe not that clear in this specific graph, but if we zoom in, there seems to be a direct correlation in this manner. So what we concluded from this is that obviously graphs with higher connectivity seems to have better anomaly detection. We're still testing this to an exhaustive extent, but that seems to be a valid reason. Secondly, lower graphs tends to have the opposite effect. We also saw that the study suggests there's an optimal balance between the size of the graph and the ability to do fault detection with that, and we're not exactly sure how to quantify this yet. Fourthly, the findings indicate that contradicting to the current belief, it's not necessarily necessary to include nodes where fault is expected. And then the recommendations further on would be to look at these types of studies, especially the effect of a time delay in your energy-based attributes, because a fault can happen in the system, and because of the fact that we're looking at energy, we might only see it in the energy data after some delay. That's from my side. Thank you.
Thanks. Maybe one question? No? One question? No? So, quick question, your method, your approach, it can be applied for different type of faults?
Yes.
Components, actuators, sensor?
Yes, it can. So we actually have been testing this method quite a while, from 2017, somewhere around there, 2017, on things like heat exchange problems, gas to liquid problems, Tennessee Eastman system. There was a CO2 system, the two-tank system that he is looking on or at. So yeah, there's quite a few systems with different types of faults, including actuator and sensor faults and so on. And it seems to work on most of them.
Okay, thank you. We can applaud the speaker again. Thanks, thank you. So the second presentation will be on learning system description for cyber physical system by, and it will be done by Alexander. Yes, you can. By Alexander Dietrich. I think the second one.
Just on the desktop, right?
Yeah, this one, yeah. So, please.
Okay, this works, I guess. Great. Thank you. I'm going to talk about how we can learn propositional logic system descriptions for symbolic fault diagnosis in the context of cyber-physical systems. So, with a very easy introduction, what I just want to do is, I have a fault, wait, there. I have a fault in my factory. I can get observations, which might be faulty in the case of faults. Then I need to reason about these, which in many cases does a human, but I want to automate this with automated fault diagnosis. And out of this reasoning comes a diagnosis. So the main question is, how can we find faults in cyber-physical systems? So all still quite easy. But when we look into this, what makes this harder is, when we look at a diagnostic system, a cyber-physical system, we often deal with a black box. We may have some information, but that may not be very accurate. So what we can rely on is, we have inputs and parameters, we have outputs and sensor values, and we know there's a fault in there somewhere. And the main problem is that I want to answer the question, how do we obtain a most likely white box model if no one tells us what happens in this diagnostic system. So we have a lot of approaches, as you can see here, where we investigated different methods. One of the papers you will see, I think, in two papers in this session. But over the years, we have had many approaches in this regard. And we try to improve upon this. And the goal of all of these approaches is, how can we get a nice propositional logic system description from data to come around this black box problem. So that's what we're going to tackle here. When we look at fault diagnosis, so maybe as a foundation here, we have the fault diagnosis algorithm, which is a propositional logic diagnosis algorithm, such as, if you know this, general diagnostic engine from Declare, for example, or Reiter's HS tree, both developed in the 80s. Then you have this diagnosis algorithm here in the middle. You have observations in the form of process data. and you have a model in the form of propositional logic. The model says, I have a weak fault model, I assume everything works correctly, I have actual sensor values, I compare this, perform some reasoning, and the difference between the sensor value and the model leads to my diagnosis in the form of a set of faulty components, which I then have to exchange. How does this look like? My process data is just a simple time series. We will augment this time series in the course of this work. And my propositional logic model is basically expressions, one after the other, of components as a conjunction that implies some observation. Also here, we will look into this further in this presentation. Just that you know what is to expected here. So let's look, how can we create these kinds of models? Basically, just in propositional logic. So what we need is, we need the process data, and from the process data to obtain information about if the system works correctly, we compute some simple residuals, which basically tell us they're 0 if there's no fault, and they're different from 0 if there's a fault. In the propositional logic, of course, we discretize this into true and false. We have some diagnosis algorithm. Here we rely on earlier work that we did. We have this diagnosis algorithm heist, which deals with continuous data in the context of propositional logic system descriptions. And it takes as input a system description and the observations, and we want to now to find this system description in propositional logic. So we want to answer if we can find the propositional logic system descriptions for cyber-physical systems that describe connections between components and observations. How do we do this? And here we have our algorithm called DDGD, which uses Granger causality. Granger causality is a method that was, I think some of you heard this morning already, was developed in the 60s. I think in the economic field first, but what it does is it looks at relationships between two signals. So here in the two signal case, signal 1 and signal 0, we look, here we have a change in this signal, it goes from 30 to 0, and then sometime later, a lag later, we also have a change here. The same happens here, and we assume, and that is the most important assumption here, that everything we know about the system is in those observations. We don't have any other information. Otherwise, this wouldn't work. So here we establish if something is Granger causal, if within a lag, which you can adjust, one signal has some obvious influence on some other signal. And that's what we leverage here. So how does our algorithm work? We don't just use the time series that I indicated, but instead we augment the time series with a second annotation. The advantage is that this annotation doesn't have to be complete. I just have to have a large enough variance in here, because here I have annotated health states. I annotate in which time step which components are healthy in my system, and I have the process data. So for example, if I know the process data changed here, I indicate that also the health state of the components changed. Same as I do here. And this is then established by Granger causality. Here, the lag parameter is 0, of course, because it's in the same lines, but this may also be in a lag somewhere above here. So the assumption in a causal manner is we could make interventions here that tell us when something is healthy and when it is not healthy, and then gain information about which components are associated to which sensors, which is quite nice. So the information we get from doing this, okay, see, it's maybe not very visible. So we have a sensor 2, which is associated to components C0 and C1, and we have a sensor 2, sensor 3, associated to component C3. And with this information, we can build such very simple tuples. We just list the components that are associated to a sensor, so they are Granger causal to the sensor. And that is the main finding of this very simple approach. We have established that Granger causality can generate tuples that describe the connections between system components and observations. And what we then do is we simply use these tuples and convert them into propositional logic expressions, which means we have conjunctions between the components which imply a sensor. And we do this for all sensors and for all components. And in the end, we have, with these expressions, our complete propositional logic expression, system description. So how do you use this algorithm? What you do is you learn this with time series, with annotated time series. You perform the Granger causality analysis. Then you generate the propositional logic system descriptions. That's what we just saw. And this gives us the symbols and the structure of our system description. And when we now want to use it, we use the same propositional, we use the same time series. We discretize it using residuals. And then we use the residuals to input this here. And for example, if sensor 2 would now be faulty, we can then conclude that it must be C0 or C1 must be the cause. And if you then want to perform minimum cardinality diagnosis, you of course would compute hitting set at this stage, but that is just for illustration here. So how does the complete algorithm look like? Driven Granger causality diagnosis is input. We have the time series, the annotated time series that I showed with the component health states and the process data. We have some threshold tau that we need. And we have the lag parameter of the Granger causality, how far in the past that looks. Our output here are the dependency tuples that we saw. And we have a couple of assumptions. We need non-stationary data. Otherwise, Granger causality does not work. We can only recognize linear dependencies. It might work with simple nonlinear dependencies, but that's not guaranteed. And the changes need to occur during the lag, which you, for now, have to find out experimentally. So what we do is you generate symptoms using, you generate symptoms from the time series by computing residuals. You apply Granger causality on the annotated time series and the lag parameter. You get out a matrix, and then you go through each element of the matrix, and you have, if you are above a threshold of those p-values in this matrix, then we input them to the into the tuples. And in the end, we achieve the tuples, and that we can straightforwardly convert into propositional logic. And then we obtain our system description. So how did we evaluate this? We evaluated this on 3 different benchmarks. We used the Tennessee Eastman process. Here, we have 2 approaches. One is using the approach I just demonstrated, which is this DGGD algorithm using Granger causality, and one where we have the Tennessee Eastman process just with expert-defined system descriptions. So if I have an expert that defines me the system description, I achieve a diagnosis accuracy of 82.5%, and I have 46 expressions in my system description. If I use the algorithm we have here, we have a low accuracy, but still hit 66% accuracy with a smaller system description. So it's a little bit worse, but we can learn it from data, which is quite nice. And also because we have to compute the residuals, of course, faults with high amplitudes we can recognize better, and faults with low amplitudes are harder to recognize. And this is a problem that is in all of these evaluations. So we also used a second benchmark, which is modeled after a real system at our university. It's basically 4 different systems for a bottling and distill process. We have here the 4 systems. If I have an expert system description defined, of course I recognize here, because we have full control over the whole systems, we recognize all of the faults, but still using it only data-driven with not even full health annotations, we get 3/4 of the faults diagnosed. Which is also quite nice in our opinion. Then we used another benchmark also of tank systems. Here we achieve, even with an expert-defined system description, not full accuracy, not 100% accuracy everywhere, but using this data-driven, we also achieve a quite nice accuracy, which also enables us to obtain good fault diagnosis. So, for the discussion, what we have a practical method we claim to learn system descriptions. Of course, we need the health annotations, but we don't need all of the health annotations. Not all of the faults need to appear in our training data, which is quite nice. But at least, of course, we need some faulty data. We can only model linear dependencies. It might work with nonlinearities, but we cannot say that it really does. We do, in causality research, we do not recognize confounders here, which is a problem. And we are missing a method that can validate these learned models, so we don't know how good they are, except we look at them as humans. But I can teaser here, we submitted a publication here, but it's not part of this research right here. So, to conclude, we have this method which uses Granger causality, which is a method that exists since the 60s, but we used it here for our system description generation. We need some annotated faults, and what we also see for the future work is that we would like to, of course, generate provably correct system descriptions, or at least system descriptions where I can have an error bound. This I don't have here, which is definitely some things to improve. Or methods that refine system descriptions with expert knowledge. This would also be quite nice. So maybe not use all of the expert knowledge, but at least a little bit more to make this a little bit more reliable. That would be nice. And but we also established, and I showed you that we have already quite some publications in this field. We do think we need more models here, because most of the research I see with symbolic fault diagnosis methods, they mostly rely on given system descriptions, and learning them like this publication does, or what Lukas Modeman is showing us in 2 talks. That would be quite nice, and I think there's still a lot of room for improvement here. So, thank you.
Presentation. So, we have time for one question, please. Question? So, one question, you talk in your presentation about a novel algorithm, as it will be applied for cyber physical system framework. My question is if you evaluate the computational complexity of your algorithm in some complex situation, complex framework.
So the Granger causality, since I have to go through, I have to evaluate at least my matrix completely with all the system is, I think, cubic runtime. I don't have large enough systems to do this empirically. So I can only look at the algorithm and on the underlying problems and establish there the complexity. But for many systems, or I didn't have systems that are large enough and that some expert can validate for me that this really works. So I had to rely on these smaller ones where I know what is correct. But that would be quite nice to have this.
Yeah. Thank you. No question? So if no question, we can applaud again the speaker. And the following presentation, the third presentation, will be on hybrid and supervised learning strategy for monitoring industrial batch, and it will be presented by Christian Frey. Please, Christian.
Okay, Professor Chudley, thank you very much. Dear audience, my name is Christian Frey. I'm with the Fraunhofer Institute for Optronic Systems Technologies and Image Exploitation, located in the south of Germany in Karlsruhe. Today, I would like to talk about a hybrid unsupervised learning strategy for monitoring industrial batch processes. Oops, wrong direction, sorry. So, industrial production processes, especially in chemical or in pharmaceutical industry, they are very, very complex. Usually you have large-scale production plants, for example, column plants, at companies like BASF or Bayer. They are equipped with a large number of sensors and actuators, up to 800 sensors and actuators, and they're very, very complex with respect to their, let's say, physical behavior. Pharmaceutical production processes are much smaller. You usually have a reaction tank of 1 cubic meter filled with fluid. It's mixed around. Additional ingredients are coming in, and those processes are characterized by a strong process fast behavior. That means you have a start phase where the process starts, then the process is, for example, heated up, mixed something, you have a transient phase, then it lasts a very long time in a stationary phase, then due to the involvement of biochemical reactions, you have changing process behavior within 5 minutes, even if such a stationary phase lasts 1 day. So, due to this involvement of these chemical reactions, it's very, very important that you monitor in one point the process phases itself and how long those processes, the process is staying in these process phases. Otherwise, you can produce a lot of fluids which you can just throw away. So the same problem as in other production plants, achieving cost-effective operation of production systems necessitates the continuous monitoring of the plant functionality. With respect to pharmaceutical processes, we have clearly the aspect of anomaly detection, finding out unusual patterns in the measured data and say, okay, this must be a fault. And the most important thing is to monitor the fast sequence of the process and the fast durations. So in the following, I will focus on the fast detection and the fast sequence monitoring of such processes. There are many algorithms which you can apply for this problem. In the following, I will focus on, I will focus on unsupervised learning techniques. One possibility is self-organizing maps. They are used widely for monitoring unknown process behaviors. There are a lot of papers. One of the first papers from our institute was 2008. The systems we developed at that time run at large production plants since that time. But what are SOMs doing? SOMs learn the data structure of unknown process, of an unknown process, the underlying data structure in an unsupervised manner. Clustering, this is a clustering-based technique. So the output are clusters within this data set. And they're projected onto a lower dimension, from a high-dimensional input space to a low-dimensional output space, usually 2 dimensions. How can these clusters be interpreted with respect to production processes? Clearly, in stationary phase, all the parameters of the process stay in let's say, in one line. And so these can be interpreted, the clusters can be interpreted as process phases. So, and another advantage of self-organizing maps is that you can visualize or extract those clusters very easily by using the U-matrix transform. So the high-dimensional input data is projected on a 2-dimensional grid, preserving the topology connections within the data set. And if you assume the recorded data of the process is a normal behavior, so the model represents the normal state of such a process. Okay, simple example. Simple example is a laboratory batch process. Two reaction tanks the process is equipped with sensors, pressure sensor, flow sensor, level sensor, and actuators, speed control pump, and a pneumatic valve. The data is recorded over 8 batches. You can see this is always repeating over the time. So it's kind of ideal batch process and nothing special. So if we train with this normal behavior, you can see over time, over the training phase, how the self-organizing map evolves, or the U matrix evolves. And you can see, okay, finally, we have found 1, 2, 3, 4 clusters. Okay, sounds cool, that's enough, but it's not really the result we expected. If we look at the control scheme, and we did not use this data for training of the process, so we see, okay, there are 5 operation steps. And what you can also see is, okay, all the process phases are nearly the same time long, but the operation step 3 is pretty short, so it's going to be suppressed or put into another process phase. This is not ideal. Simple example, so, or the main problem of self-organizing maps, or also algorithms which do it kind of similar, also neural gases or something like that, is that they strongly depend on the training data set. So if you have strong correlations between the process values, this will be a problem. And especially if you have, let's say, an unbalanced training data set, this will give you not a good result when training such models. So just a simple example, synthetic data set for stationary process phases, for transient process phases. The stationary process phases are 180 samples long, the others 20 samples long. We have, you see the time course of those 2 process values. Yeah, clearly this should come out 8 process values, 8 process phases. But yeah, if we train it with a standard SOM algorithm, you will end up in 4 process phases, the other got omitted. And even you cannot use the quantification error for anomaly detection, because the transient process phases are interpreted as error. So there are other, let's say, unsupervised learning mechanisms, as for example the instantaneous topological map. I will not go into detail of this algorithm, it's kind of complicated, but what does this algorithm do? It also is topologically, is preserving the topology of the training data set. So if there are clusters in, there will be prototypes generated and there will be connected by edges. And the shorter the edges are, the closer or the more each the prototypes belong to one cluster. So, but it does not project the input data set on a lower dimension, like for example onto a two-dimensional grid, like self-organizing maps. It keeps the description of the clusters in the higher dimension. So it has advantages, as stated. It can handle correlated data, and especially it can handle unbalanced data sets. So the output of these algorithms are also prototypes, like of the self-organizing map. But you can, in that sense, those prototypes are kind of resampled data set. So we're going to use this mechanism and use it for a better process phase identification. One point should be noted: the algorithm is very cheap. Okay, it is not iterative. It is sequential, and it has just one parameter, the so-called hyperparameter. It describes the volume of the hypersphere which you put data points together. So, so now the idea is to combine an ITM with a self-organizing map. What are we going to do? On the raw data, we apply the instantaneous topological map. And the output of this algorithms are prototypes. They are kind of resampling the data set. We do not use the edges, but we do use those prototypes for anomaly detection. This is very precise. And but we do use the prototypes also as input data set for the self-organizing map. So, and then you have kind of a balanced data set, which then you can, with a synthetic data set, it's very simple, you will find those 8 clusters in the data set. So this is is correct. And you can also use the ITM, the quantification error for anomaly detection. So going back to the laboratory process. Okay, here we have recorded 4 training batches, T1 to T4, and 2 evaluation batches, and we took out of the control system, hey, which process fast we have, just for comparing the results. So after training, you end up in 5 process phases, in 5 clusters in the self-organizing map. These clusters are automatically found. You can find it in the paper by watershed transformation and automatic leveling of this watershed transformation. And the self-organizing map is not a simple self-organizing map, it's a self-growing one with also very robust growing algorithms. So what you can see in the lower time course, the green one, okay, is the output of the proposed method. Okay, clearly you find those process phases and also the process phase sequence is correct. Compared to the standard sum in red, it's not correct. You cannot use it. So why are we going to do that? That seems also, okay, for what? So in pharmaceutical industry, the processes are pretty, let's say, unautomated. So you have those reaction tanks, and okay, the operator opens this tank and puts something in, and then 5 minutes later, after a biochemical reaction starts, and the process behavior changes completely. So if those biochemical reactions do not work really good, and the production process for one batch takes 1 week, so you must it's of utmost importance to find out, is the process fast sequence correct, and is the process fast duration correct? And if not, you can just throw the whole liquid away. So what they usually do, if we assume those T1 to T4 are the very good processes, they call it golden batches. We model those golden batches and find out, okay, they have from 1 to 5 process phases, and the process stays in phase 1 for 1 day, in phase 2 for 20 minutes, and so on. So, and with this information, we can monitor the process phase sequence and the process phase duration. So batch P1 is a good one. You can always see the green bars, or it's difficult to see, are the golden batches, how long they stay and how the sequence is. And you can see, okay, batch 1, P1 is correct. They are all lying, the time is lying within the threshold. And the other processes, they differ from the supposed time within the distinct process phase. So, and then you can just stop this process without keeping it running for over 1 week. So I'll come to the end. Okay, limitations of some unbalanced data sets, correlated data is not good. You will end up, especially if you find all clusters in the data, you will end up in, that's not correct. Hybrid, unsupervised learning strategy, using other unsupervised learning mechanisms, like for example, instantaneous topological mapping, to generate, let's say, a resampled data set, also topologically ordered, and use that as input for the self-organizing map. We've done several studies which compare the health to the standard sum. There might be other algorithms we haven't compared to, okay? Now, at the moment we are testing the systems at a large scale chemical plant, and yeah, it is promising. So far to now, thank you very much.
Question, please? Any question? Some question? No? Just maybe one question that I can't understand. You talk about scenarios, scenarios where you talk about imbalanced data and highly corrected. What about corrected data, and how corrected data when you
Correlated data?
Yes. And corrected also with data with faults and with maybe some noise. How you deal with that, and how you can evaluate the superiority of the proposed algorithm, taking into account the complexity of your the problem.
Okay. Okay. Correlated data, especially in chemical industry, when you, for example, have a reaction tank, and you heat it up, okay? There might be two process values be strongly correlated. This might be the pressure and the temperature. And usually that gives you a problem when training such unsupervised learning algorithms. Was the first part. The other point is the complexity of the system. Did I understand the question? Yeah. So what you're going to do, I was talking about large-scale production plants with 800 sensors. So you will not use such a model on 800 sensors. Usually what you're going to do if you have such big production plants, you make process units. They are logically also controlled often by one controller, and they're succeeding steps. So, and usually you go down to that level, okay?
Thank you, Christian. We can continue our discussion after.
Yeah.
No question? One question? Yes?
Thanks for the presentation. I had a question about processes that are quite dynamic and fast. So imagine you're monitoring the pressure on your process and you have a bunch of spikes which are expected. Would you think that self-organizing maps would work in that case?
So
or
disturbed process values, strongly disturbed process values with fast changes?
I'm not sure what you define as disturbance, but that is part of the process you would expect. So those spikes that you have in pressure are some valve openings, so you do want to have that.
Yeah.
So in that case, would you think that SOMs would work? Or if not, what pre-processing would you be? Okay.
It strongly depends on how fast your process is and how fast your sampling is. You know?
Just say, no problem from sampling point of view. So just imagine you have a highly dynamic system, like you do not have any problem from the sampling side. Just the nature of your process is quite malplaced. Fast in a sense that has abrupt changes, you know.
That's also, that does not make a problem. You're just focusing on another time scale, you know. While these processes we are talking about in pharmaceutical industry, they're so slow.
Fair enough.
Even the pressure measurement it looks like, okay. So, fair enough. But they also have quick changes. If the pump is stopping, if the valve is closed, that's also the same. So yeah, should be no problem.
Okay.
We had that done for a motor controller, also with self-organizing map, and they are switching really fast.
That is true.
And sometimes they switch not that fast. Yeah.
So you would claim that it would work?
Try it, yeah.
Okay, great. Thanks.
Thank you for your question, and we can continue the discussion just after. So again, thank you, Christian, for your presentation. So the next presentation is about deep learning-based discretization for model-based diagnosis. And it will be presented by Lucas Mudman.
That looks good. So yeah, thank you for the introduction. Today I want to present our paper, Deep Learning-Based Discretization for Model-Based Diagnosis, where I want to give you an introduction in our methodology, Discrete to Die, where we want to go towards an automated generation of diagnosis knowledge, and in the end, go towards also an automated diagnosis in cyber-physical systems. And that was the wrong direction, and that's it. So, also when my colleague Henrik Steuder presented his paper, he talked about our use case, so the International Space Station, and it is, let's say, a cyber-physical system in a pretty complex way. But what can we expect as a data from this CPS? We just get time series data. So we are able to process anomaly detection, so generate symptoms. But then we will run into a gap. So how can we go further? We have seen in a talk from Alexander Dietrich that we're then in the diagnosis part using symbolic AI. So we are there with the ground information of time series data, but we lack information about the symbols, the causality, how we can describe the normal behaving system. So here we have somehow a description how it could be formulated, as it could also be within the ISS. In this case, we have a core that is dehumidifying the air within our system, and there are causal acting components on our observable core that are causally related on it. We can transfer the information about the systems to the system description, but we lack the information about the components and, for example, then the system that we observe, that we want to observe. It was also a part of the talk of my colleague Henrik Steuder. There we had prior information about the diagnosis rule, and there he processed his anomaly detection for. What are the challenges there? In diagnosis community, mostly it is said, also what Alexander said, the information is mostly given. But when you have such a complex system, and an old system, that's now up to 25 years, I think, in space, there's also a fluctuation of system experts. The system is changing over time. And when you just change one part within your system, you have to reiterate through your diagnosis knowledge, through the system description. Such that it would be interesting to automate everything on that. And our interest is to do that by discretization. To go from the time series domain, given some signals, into the symbolic domain. So, but there are a few questions that we have to ask ourselves. How can we discretize highly complex, high-dimensional data? How is our input, and how could it look like in a symbolic domain? On the other side, how can we generate residuals? And how can we detect then the anomaly or the symptom? In the end, also, the left side of the diagnosis rule that is mostly pain. And Alexander told us in his talk about finding causal relations on that. And in the end, how to connect everything together such that we are reaching a logical rule that is capable of, or that can be used for logical satisfiability solver in diagnosis. That's the theory. Now we come to the approaches. Especially, we have asked ourselves the discretization part for all the time series data that we will get from the ISS. How can we discretize that? And from the state of the art, we thought about our variational autoencoders capable of doing that, since they are built to encode high-dimensional data in a lower dimensional space, such that also these information could be interpretable by the system expert, so that he also relies on the system that we will give him for diagnosing the system. But when we think about variational autoencoders, they're mostly used with a latent space or a prior that is represented by a Gaussian latent space. So when we're taking a Gaussian latent space, we are far away from discretization. It is continuous space. And when we're thinking about discretization itself, when we're thinking just of a discrete latent space, we have the problem of the training of the variational autoencoder. We need back propagation, and that needs a differential distribution. So when we have a binary latent space, the differentiation of a binary is 0, and we're not further in our way to reach automated diagnosis. But there is a work from Young et al. That proposed an approach that is called Gumbel softmax distribution, and there we can realize a sampling of a categorical latent space, such we are now able to train a variational autoencoder with a discretized latent space. How is it working now in our setup? We have as input a vector of signals at time t and encoded with a prior of an equal weighted categorical distribution. You have a hyperparameter of saying, okay, you give a free space of 20 or whatever. After that, there comes the variational part. We approximate with the Gumbel softmax distribution the categorical latent space into a differentiable distribution, such that we are able to encode, to decode the information back again and reconstruct it then into a mean and a variance. Why mean and variance and not just a point? In our case, we thought that we can also solve the problem of the residual generation by using the categorical variational autoencoder, such that we are saying we have the distribution on the reconstructed side given some input, and then we can calculate the likelihood, how likely the point, the reconstruction, is given the input data, such that if we have a very low likelihood, we can say there is something wrong in the system. how does it look like when you process that? So we have here on the left part our input data. That's a pretty simple 3-tank system, and we put that inside our autoencoder, and within the latent space we have the sampled categorical distribution, or approximated through Gumbel softmax, and calculate the max argmax such that we can find the category with this index. And that's somehow looking then like this. And on the right part, we have then the residual that is represented by the likelihood. As it is always an anomaly detection, we need to define some threshold. And as we are doing their unsupervised learning approach, learning it on normal data, we can say, okay, with the learned data, we can see what is our minimum likelihood, and then detect then there the anomaly when it is underneath that threshold. All in all, our methodology looks like the following. We have the input data, time series data at time stamped t, and we discretize it like I previously presented with the categorical variation autoencoder. We have our byproduct, let's say it like that, the residual, and we can convert that into a Boolean, such that we can say at some point our knowledge base is inconsistent within the diagnosis part. As we are here in these two parts, generating the information separable, we needed to combine them such that we are ending up in a logical rule dependency relation, and that we are doing at the moment with association rule mining. Up to now, we have automated the right part with SI, the modes that we're generating from our input data, and the residual. The part of the left part is just the complicated part that Alex presented before. We, up to now, say we have this expert knowledge and insert that according to the state we are finding. In the end, this is then a rule consistent to the rule how it should be look like for a satisfiability solver. That's the theory for the methodology coming to the evaluation. As we are plugged in together several parts. We have evaluated at first the discretization and the residual generation disciplines, and compared it to a baseline model that was here, a Gaussian mixture model. Our datasets have been the bare-people dataset that was a dataset simulated from a colleague of us, and two real-world datasets, the SWOT dataset and a dataset provided by Siemens, but it is also publicly available. What we can see here, the categorical variational autoencoder looks pretty good within its solutions. We can say we find a meaningful amount of states within the system, such that we have not every single timestamp a different category. Then it makes no sense, and the rule base is just annoyingly big. In comparison to that, it is in the nature of the GMM algorithm that you have to provide the algorithm with a specific amount of Gaussians, and also the Gaussian mixture model is taking these, such that you cannot find the meaningful amount of rules. It's just taking everything. On the other side, the residual generation, there the GMM is outperforming our algorithm. Looking to it now, it can be explained by the use of its distribution in the latent space. The categorical variation autoencoder is just using a categorical distribution, such that there can be less information encoded as when you use a continuous distribution or several continuous distributions like in the Gaussian mixture model. Evaluating the complete methodology, discrete to die, we have there taken a 3-tank simulation. Probably there will come the question, why not on the 3 different data sets I evaluated the other parts of the system. It's just because we are not system experts. This system, I can build the ground truth, but up to now, I'm not sure whether my ground truth is also ground truth that the engineers thought of. So from my perspective, when I've been in industry, you ask 3 persons and you get 3 different answers to that. That's just interpretation. But what we have seen here, we have simulated a 3-tank data set with a different states. So the first state is Q1, inflow, then an exchange between tank 1, tank 2, exchange between tank 2 to tank 3, and so on and so forth. What we have done then, we simulated the normal behavior several times until we are at a saturation level, and then inserted the anomaly cycles. 1 cycle and also 3 cycles, just to see wherever our residual generation has there a gap, such that we can see wherever our anomaly detection or residual generation works good or not. But what we can see is when we have the anomalies inserted in Q1 state, all these Q1 and V12 have a big magnitude in its anomalous behavior. And we can find the right diagnosis or root cause. But in case of V23 and V3, we have not that big magnitude, such that when we're simulating it with 1 cycle, we cannot find the right root cause, but when we are simulating it until a certain magnitude, we are able to do that, such that we can say the methodology is working, but there are gaps that we have to refine. And so also coming now to the key takeaways and future directions. What we could show within this paper is that the categorical variation autoencoder is capable of capturing complex relationships, such that in a high-dimensional data set, we can find a lower-dimensional representation. And we could also see that it is somehow related to a mode of an automaton. What we also could show is that we don't have to refine every single time when a new component is inserted, that we have to refine all the rule base. We can relearn the data, the model, and we just have to insert the heuristic knowledge in the end. But that's one gap I want to fill in the future. One drawback is that residual generation is not working properly. That's also one point for the future direction. We have to enhance the residual generation. I want to also incorporate automated learning such that we can also find wrong transitions, and also the part of Alex should be somehow inserted such that we get an automated diagnosis rule generation. That's it. Thank you.
Thank you, Lucas, for your presentation. One question, please.
Thank you. I would like to know how you are taking into account the dynamics in the symbolic models yeah, the fact that you have a dynamic system.
Yes.
Are you taking this into account with the specific signals, with by derivating some signals, or how?
No, not.
No.
We're learning the system as it is, so as we are getting such that in that state, how we get the data. And the dynamics are within the learned model, or in the learned state discretization. But when you're thinking of the residual generation, we have seen it is not working.
Yeah.
Because we are not properly reconstruct the data because of the pretty narrow latent space, such that we have not so much information in it. And that's one point we want to enhance in the next paper, something like RNN-based sequence-to-sequence models, that we can find patterns and also have more information in the latent space, such that we can find also small anomalies.
But maybe you should consider also to use either some derivatives, but they are often difficult to calculate, or some integral of the signals that you get, because I mean, it's easy to understand a derivative would indicate that there is a growing signal, and yeah, it's symbolically it can grasp some information.
Yes, I will try, yes.
Okay. And then just to comment, a long time ago, in the qualitative reasoning community, there has been a lot of work in providing symbolic models, either with sign algebra or with order of magnitude algebra. And so it comes back to getting this, exactly these models, but it was done from the knowledge of the physical relations, of the equations, actually. But it would be interesting to compare what you get with what is got by this kind of approaches on a simple system. It would be interesting.
Okay.
Yeah.
Yes.
Yeah.
Thank you.
Thank you.
Thank you, Louise. Yes, related to the question of from classical fault detection and isolation methods, the problem is how to improve the sensitivity on residual generator on faults, and how to improve the robustness on disturbances. In your case, using the deep learning-based discretization, how we can evaluate the sensitivity and the sensitivity on fault and the disturbances and the robustness on disturbances? We can evaluate that or not? We can compare with classical methods? Because you talk in your presentation on residual generators.
This one?
My question is about the sensitivity of the residual generator on fault and the robustness on disturbances, because when you have a signal, you have some faults and some disturbances.
Yes.
Do you evaluate or compare with classical method?
No, absolutely. Okay. So residual generation was GMMs I've compared.
Okay.
That was the comparison there, but up to now, not more than that.
Okay. So thank you, Lucas, for your presentation. So the next presentation is about transforming time Petri nets into heterogeneous Petri nets for hybrid system monitoring. It will be presented by Leonie Heitz from the laboratory of LAS laboratory, the University of Toulouse. So you can start your presentation.
Hello everyone, thank you for being here for my presentation about transforming time Petri nets into heterogeneous Petri nets for hybrid system monitoring. So as we said before in some previous presentations, industrial systems tend to become more and more complex, and so with that we have a complex maintenance in terms of diagnosis and prognosis. So for that, the number of formalisms has increased. First with the hybrid systems who have discrete event evolution as well as continuous dynamics. Then we have time Petri nets, TPN, that explicitly express time constraints but do not express continuous nor hybrid dynamics. And so we needed to come up with a new formalism to express hybrid systems under time uncertainties. And so the team developed the HTPN, which stands for heterogeneous Petri nets. But as defined, the HTPN do not explicitly have time constraints as TPN have. And so the goal of this presentation is to show you that the HTPN can explicitly express time constraints as well as TPN. So to prove the equivalence between the TPN and the HTPN, we will see three parts. First, I will introduce you to a subclass which is called THTPN for time heterogeneous Petri nets. Then I have to define a transformation function between the TPN and the HTPN, and if I can prove to you that this transformation function is a bijection, then it means there is an equivalence between the two formalisms. But before doing that, I have to bring you a little bit of context. So a Petri net is a mathematical way to describe a system, and a time Petri net is a regular Petri net with added time constraints. These time constraints can be found on the places, the transition, or the arcs of the system. The choice of the formalism depends on the utilization we do from what we want to do with the formalism afterwards. For example, the TTPN, so the one with the time constraints on the transition, have a computational advantage because we can simulate them with some tools existing, like TINA, for example. So this reference, this article from Boyer and Roux in 2008, is here to compare these three formalisms. So first, I have to tell you about strong and weak semantics in time Petri nets. So for example, in weak semantics, you do not force the firing of a transition. The transition remains fireable for an infinite time. But in a strong semantic, you have to force the firing of the transition whenever you reach the upper bound of the time constraints. So the first theorem says that the strong semantics of all TPN types, so place, transition, and arcs TPN, are strictly more expressive than their weak semantics. For example, that means that a PTPN in weak semantics can be transformed into a PTPN in strong semantics. Then the theorem 2 and 3 says that the TPN with the time constraints on the arcs are strictly more expressive than TTPN and PTPN. So that means that by transitivity, we can say that the time Petri nets with conditions on the arcs in strong semantics are strictly more expressive than all other kinds of TPN. And so that is important because for my proof next, I will focus only on the arc on the time Petri nets with the conditions on the arcs. So this is a non-mathematical representation of the expressiveness, but it's just to give you a little bit of understanding. Then let's talk about heterogeneous Petri nets. So they were developed in our team in 2022. So they are an extension of Petri nets, and they were developed to model, simulate, and monitor hybrid systems under uncertainties. So here in heterogeneous Petri nets, places are associated with two dynamics, a continuous dynamic and a degradation dynamic. Then each token have three attributes. One that we call the configuration, the continuous state vector, and the degradation vector. This idea comes from colored Petri nets and Petri nets with objects. So in heterogeneous Petri nets, we added the token status, so a degradation information. This is not found in other kinds of Petri nets, and this is one of the advantages of heterogeneous Petri nets, because it can help to monitor diagnosis and prognose the system, as well as computing the remaining useful life of the system. So this is the mathematical definition of an heterogeneous Petri net. You can see that each arc of a heterogeneous Petri net is associated with a triplet and a weight. The weight is the number of tokens needed to fire the transition, and the triplet has a symbolic condition, a numerical condition, and a degradation condition. There are three conditions because there are three attributes in each tokens. So each arc coming from a place to a transition is a condition arc, but each arc from a transition to a place is an assignment arc, which assigns values to the token produced downstream of the transition. Now that we have all the context necessary, let's go to my contributions. So as I said earlier, we will focus on the ATPN in strong semantics for the mathematical proof. And so first I will introduce you with a subclass of the THTPN before going to the rest. So here is a simplified version of the HTPN. It's the THTPN where each token has only one attribute that we call theta, and it's the clock of the token. There is no other attributes in the tokens. Then each place is associated with one single dynamic, which is a continuous dynamic, and which allows to implement the token clock. And we do not bring any symbolic condition nor degradation condition, just to facilitate a little bit the proofs afterwards. So, as I told you, I have to bring you with a transformation function between an ATPN, that you can see on the left, and a THTPN on the right. So my function is called f, and the idea is to take the same structure in both systems, take the same initial marking, reduce the attributes of the token to only the clock of the token, and change the labels on the arcs to add the triplet, but with no symbolic condition, no degradation condition, only the numerical condition on the clock of the token. And the condition resembles a time constraint. So we were able to prove that f is injective. That means that when you transform ATPN to a THTPN, two distinct elements in the TPN world cannot have the same image by f in the HTPN world. Then we were also able to prove that f is surjective. And that allows us to say that f is bijective, so we can bring f minus 1. So we can also do the transformation in the other way. And that means if there is bijection, then there is equivalence between the ATPN in strong semantics and the THTPN, our subclass. Then we were able to to add a tool prototype to this. So here I talk about HEMU. It's another advantage of the HTPN because the HTPN, the heterogeneous Petri nets, were bring with a Python-based software that is called HEMU, and that can simulate, diagnose, and prognose those kind of Petri nets. So what we did is that we developed a Python transformation code. So it's an automated code that can transform a TTPN into an HTPN. So remember, before I said that we were focusing on the ATPN, but that the TTPN had a computational advantage. So what we wanted to do is to start with the TTPN because we can put it inside a software like Tina, for example. We have a code in a TTPN, and then our code is able to convert this TTPN into a THTPN. Then we can bring expert information. So an expert can come and bring information inside of the code to add, for example, degradation information. Then it's a HTPN. And then we can feed it into HEMU in order to simulate, diagnose, and prognose it. So we were able first to bring a transformation function between the two subclasses of the TPN and HTPN. Then we were able to prove a formal equivalence between the ATPN and the THTPN and to provide a Python code to transform it. The next step now would be to add a little bit of code to do this part of the transformation. This function exists in the paper of Boyer and Roux that I talked about before. But it's not explicitly coded inside of the software that we did. So this is the next step. And thank you for your attention.
Thank you. So, thank you for your talk. I have just a question about the name degradation status. Yeah. Is it a name that has been chosen in the specific context of diagnosis? And could it be called just a mode? In fact, it is, as far as I have understood, it is some discrete, some symbol characterizing an operating mode. Is it right or not? And by contrast with the other attribute of the token, focusing on the constraints on continuous values.
Actually, the degradation is a continuous value because it is changing according to a continuous dynamic. And so for some systems, we can know the dynamic of the degradation. It is known that some components have degradation, and we know how it evolves. And so we can, and so we can compute the degradation out of this degradation dynamic. I don't know if...
So it is one way to characterize degradation, and the mode remains the place in the Petri net.
Yes, completely.
Okay. Okay, thank you.
Another question? No? So thank you, Leonie, for your presentation. Okay. So the following. The following presentation will be on VNet. So this work presents an actualization of the formalism VNet, and it will be presented by John William Vasquez. So, please.
Okay. Good afternoon. Thank you for being here in this presentation. For me, it's a pleasure. Okay, thank you. Good afternoon, everyone. For me, it's a pleasure to be here presenting this new formal model of discrete events systems. This is the first time that this model is presented in this Congress. Then I'm very happy. I'm very happy with your presence. Then let's go to begin. The content of the Congress, of the presentation, let's go on one introduction. After, let's go to talk about the vignettes, an example, a case study, and finally with the conclusion. We go to talk about some more specific concept in discrete event system, because it is a solution and problem that I detected. First of all, we have control system and supervisory system. The control system includes control actions and components, sensor actuators, and controllers, and focuses in real-time control tasks. And supervisory system provides an oversight of multiple control systems, coordinates and monitors the processes, gathers data, displays information, focuses in optimization and fault diagnosis of the systems. Then, really, the Petri and the automata are more related to control system, and they can be used for diagnosis, but it's more specific for control systems. This is a framework that I use for analyze this situation. That in our physical systems, we have sensor and actuators, we have inputs and outputs and control algorithms in all our process. Then here we can analyze this process as a sequence of discrete events. In these sequences, to supervise, we can detect occurrence simultaneity of discrete events, partial recognition of events, repetitions events, false positive, another situation that I go to explain before. For what? For generate alerts or alarms to identify what happened in the process. Here we begin to define what is an event. An event is an event type that occurs within a date. A sequence of the events is an ordered set of time observation of event types. Then here we have an example of simultaneity. In language theory, the simultaneity is not possible, but in the real life, it can happen. But for example, you can put two letters at the same time. But for example, in Spanish, you say A and E, but in English, you can say that is a mixing the A and I, and then it is possible the simultaneity of letters in the real life. Then here we have two events that occur at the same time, an event that occurred before, after. Then here we can see that a simultaneous occurrence is defined as the representative situation when two or more events occur simultaneously, or the dates is extremely closely that can be assumed as simultaneous. In this Petri net, if both events occur at the same time, we really don't know the Petri don't identify it. Automata also don't identify if the event occurs at the same time. We can detect this with these formal models. Now, the partial recognition of sequences. We have a temporal pattern, like a Petri net, automata, or a chronicle. If I have a sequence of events, but here the event A is recognized, B is more too late, then it's not recognized, and then this model don't recognize more events. Stop there, nothing. Here in this automata, A, B, C, F don't occur, and G occurs, but it is not recognized because F don't occur. If sometimes it's assuming as a fault, but it is not a fault. It's an event called if. And now another, the false positive is when occurs more events than the events that is needed. For example, the correct trace is A, B, C. Only 3 events, 3 times. Only 1 time each event. But here occur A, E again, B, B again, E, and C. And this trace is assumed as correct for this Petri net. But sometimes it's not possible in a system. Maybe, for example, you can take one beer, one bottle of beer, wine, and another beer. A beer, a wine, a beer. It's many alcohol. Then, if you need detect only 3 events, your formal model need that recognize only 1 event, only the events that appear in the trace. With the automata, is the same situation. Now I go to present the formal model VNet. The formal model is an extended and improved model of the chronicles. We represent a new formal models to manage discrete events, and it has a graph that we can detect the evolution of the events. The tuple is ETG, init, N, frag, R, TL, EVA, the time of the evaluation, that it is the set of event types, T is the set of temporal constraints, G is a direct graph, which E is the set of event type on the graph, arcs represent the different time constraint between the events, if is a function of activation or deactivation of the arcs according to the evolution of the event sequence. We go to check it next. Init is the first event that initiates the VNet and corresponds to the event type that ends the VNet. In a VNet, it's possible that the initial and the fill events are the same, or are two events that initiate. Frag corresponds to the set of frequency of the events. How many times are repeated the events in the VNet? Arc contains the set of logical predicates that correspond to the restriction and warnings that confirm the VNet. And the time of the evaluation corresponding to the maximum time accepted to receive time observation after that the first event occurs happening in the VNet. The occurrence matrix is a timeless representation of the possible events. We have here an example of a VNet. The first event is A, and the second event B and C. We have had a time restriction of 0, then they can occur simultaneously, then init A, En, B and C. Here he is in the event sequence. Another possible order is A, B, C. Another possible order is A, C, B. A, C, B. Then this is all the possible with the time restriction that is possible. We can modulate with this matrix the order of the sequences. And here, an VNet is partially recognized calculating the quantity of event recognized with the quantity of time observation. We had this is another example, the event A and C must occur at time simultaneously because the time restriction is 0, then A, C, and A. After B and D, the time restriction is satisfied, then it's recognized. But here, C occur after of E. Then it's 75% of the recognition of the VNet with this event sequence. Here is the formal description of the VNet. For example, this VNet with one arc, this, then the set of 7 types, and the set of time restriction. Here is the time restriction 1. One is the frequency, the first time of occurrence of A, and the first occurrence of B. We have a time restriction from 1 to 2 time units. The maximal frequency for A and B in this VNet is 1, only can occur one time. The time of evaluation is 2, and the recognition is when B or time be recognized one time that occur. Here we have a VNet with 2 arcs. Looks like here this arc of A go the 1 to 3, then I is repeated 3 times, and after those 3 times B is repeated. B occur 1 time. Here is represented the 2 time transition. Look, the maximum frequency of A is 3, and the maximum frequency of B is 1. Time evaluation 6, and there is recognized when B arrives one occurrence. Here we go to see the evolution of this model. In this example, the arc is inhabilitated, and here we have the possible occurrence, the first occurrence in this VNet. Then occurs A, then it is activated, and we wait the next possible occurrence. When occurs B and satisfy the time restriction, this incrementing in 2, and we're waiting for the next possible occurrence, but in this case occur B. The VNet can identify in parentheses the occurrence of B, but it's not the order in that must occur B. Then it's a good information for detect. And the next possible occurrence is A, is occur and satisfies, and the final occurrence looks like here, arrange the 3 times of A, then it is disactivated, and is activating now this arc for the next occurrence that is B. B with the time restriction, and occurs B, and in final, the B is recognized by 18%. Why? Because there are another B, and guarding an additional B, and the B is recognized. Now, let's go to see a case study. I use this model in alarm management because the alarms in the system is very useful, recognizes the order of the alarms. In this example, in one hydrogen plant, we had to monitor 2 alarms, one of power supply failure and another of hydrogen gas leak, A and B. And here we have 3 sequences for learning or for construct the temporal model that we can detect that the first event that occurs is A, after B, B, and A. Between the first and the second occurrence of A, B, 1 and 2 time units, and between B and B, the first occurrence of B and the second occurrence of B, 6 and 7 time units. Only occurs 2 times A and 2 times B, and this is for a normal, it's a normal sequences of these alarms in a startup procedure. Now we have here the 3 model with a time Petronet, with an automaton, with a chronicle. All these sequences can be recognized as good sequences in these models. But we can check that alpha is a representation of the occurrence of A and B at the time. Then it is a possible failure that the other model don't detect. Now the solution with a Petronet is this. Then we have A at the first and the final event. This is the occurrence matrix A, B, B, A. Then with the frequency of A is 2, warning that is not possible on simultaneous occurrence. Here we have the transition, the events, the maximal frequency is 2 for A and 2 for B. The time of evaluation is 11. And here we have with the other sequence that the Petrinet and the Chronicle and the Automata was recognized as good. Here in this VNet is recognized at 75%, 50%, this 0% with these alarms. Okay. And this is a good sequence that is recognized at 10%. As conclusion, VNet offers a good option for detect supervision in industrial process. Compared with other formalities, we can see that this model can handle and can manage simultaneous occurrence and the correct order of the events. And the idea is to implement this type of model in industrial processes. We go to work, I am working in the simulation of, prove the simulation of deep VNets. If we can have too many event sequence run with only 2 events, I am calculating with 5 event types in 30 time points. Supercomputer that we have in the university, we have 1 year in simulate all the millions of possible event sequence. Then we are simulating this possible event sequence, and the VNet recognizes which sequences is good. We are working in that. Then thank you for being here. And this query for give me your email and be in contact with you if you are interested in continuing with this team. I hope to create a community for work with this new formal model. Thank you so much.
One question? Stop.
Yes, thank you for the presentation. When using the approach you propose to quantify or discretize or obtain sequence from continuous signals, which may be noisy, what about the effect of noise at the transition between discrete values? You talked about frequency within the well, is it well suited for that problem, yes, or what is your opinion about this?
It's not the problem of my formal model. It's the problem of acquisition data. For example, for detect the I am writing a new paper when I'm formalizing all the theory of this model. And in the time point, I propose a 5% plus and less. If the events occur at 5% of the time between the time points of the frequency, then if it occurs sometime, what you say, if occurs similar, then it can detect it as, yes, it can be an approach for the starting time. This is the problem because all the events can occur at the same nanosecond, the millisecond. It's hard to synchronize that. Then I propose formally one window bandwidth for the events can be matched with the time point. Yes, this is.
Thank you. Another question?
Okay.
So, thank you for your presentation.
Thank you.
So, before closing this session, thank you for all the speakers. Thank you to the audience, online and offline, for your presence. Thanks to the organizer for this nice conference, Silvio, Christina, and all the International Program Committee. and the National Organizing Committee. So this session is now closed. You can enjoy the break, coffee break before this, the last session and the last session of the day and for the conference. So thank you for your presence.
streaming.
Good afternoon. My name is Abdelrahim Lamrani. I am postdoc from Aix-Marseille University. I would like to present our work entitled Finite Frequency Phase Fault-Tolerant Static Output Feedback H Infinity Control for Diesel Engine Air Path System. In beginning, we will the following outline. First, the introduction. Next, diesel engine air path model. After that, finite frequency static output phase control strategy using descriptor approach. After that, simulation results. Finally, the conclusion and the future work. In this paper, we present a model of diesel engine air path system. This model consists of 4-cylinder and intercooler. PC is the compressor power. PI is the intake manifold pressures. PX is the exhaust manifold pressures. PT is the turbine pressures. WXT is the mass flow rates. WXI is the turbine flow rates. The main objective of this paper is to regulate the intake manifold pressures and exhaust manifold pressures to desire the reference pressures by controlling the valve geometry turbine, VGT, and exhaust gas recirculation, EGR valve. So this proposed model is given by equation 1, where the following from structure is given by 2, where PE is the intake manifold pressures, PX exhaust manifold pressures, PC is compressor power. The numerical example for diesel engine air path model exists from this table. Define x1 equal PA, x2 equal PX, x3 equal PC, compressor power, are the state variable. U1 equal valve geometry turbine, U2 equal exhaust gas recirculation is the controller input. WT is the fuel injection, denote the disturbance input. Then the state space of the diesel engine air path model is given by equation 3. The energy of disturbance WT is estimated to be dominated for no finite frequency domain omega. Where the following from parameters is given by 5. The parameter rho of T are defined as follows. These functions are bounded by Pi between Pi minimum and Pi maximum, Px between Px minimum and Px maximum. Obtained equation 7. From this decomposition, we have the following function. These functions are governed by the property of convexity subclass. This leads for local model by combination for function. And finally, Hi rho of T is seen as the normalization height of each if the rules given by equation 11. We have the fuzzy model proposed by equation 20, where the matrices I and B as well. This figure proposes the comparisons between intake and manifold pressures, exhaust manifold pressures, and compressor compressor power. But by MATLAB Simulink and AMSIM software. We define the integrator of tracking error, the proposite fault-tolerant static output feedback controller is given by equation 14, where the fault matrix G is defined as, and K1 and Q2 are given subform structure. Combining the fuzzy system and the static output feedback, we have the closed-loop fuzzy system, where the following from parameters. Our objective is to design the static output feedback controller such that two conditions are satisfied. The closed-loop fuzzy system 50 is absolutely stable, and the following H infinity performance. For unknown fault matrix G and output feedback controller exist, such that the closed-loop fuzzy system is absolutely stable with H infinity fault-tolerant performance index gamma defined positive, infinite frequency domain. If there exists the matrix R P defined positive, Q defined positive, and F satisfying the following condition. To linearization the theorem 1, we define the following matrices are given by this equation 21, 22, and 23. We have theorem 2. Closed-loop fuzzy system 50 is absolutely stable with H infinity fault-tolerant performance index gamma infinite frequency domain. If there exists the symmetry matrix and satisfy 24, where the matrix Psi and Phi defined in the original paper. If you take Q do H equal 0, we can apply theorem 2 is subtly to fault-tolerant static output feedback air path H infinity control for diesel engine using descriptor approach in the fuel frequency domain. By solving the condition of theorem 2, we have the parameter of the fuzzy controller matrix. The fault is stuck as follows, and the pressure variation ranges is given by equation 27, and the fuel flow rates are given as follows in the finite frequency range. By solving the condition of theorem 2, we have the following finite frequency fault-tolerant static output fuzzy controller matrix given by equation 29. The intake and exhaust manifold processors are given in this figure. We can see from this figure the ground tracking and fast convergence for two methods proposed in this paper. This figure provides the valve turbine flow rate, VGT, and gas and exhaust gas recirculation flow rate. The conclusion, the new finite frequency H infinity static output controller is proposed for the diesel engine system using descriptor approach, and the simulation result demonstrate the effectiveness of the proposed approach. The fault-tolerant LPV, finite frequency dynamic static output control for marine diesel engine, they will by our future work. Thank you.
Any questions? We have 10 minutes for questions. Quickly.
Short.
Now it will be better. We have to turn on the microphone. So, because you jump very quickly, 10 minutes, it was a mistake from your side, because now we have to ask you questions for the next 10 minutes, yeah? So this is the issue. And could you elaborate a little the things related to the premise variables that you had? I mean, are they measurable or not? And then, if you will answer this question, can you summarize a little bit about the membership functions that you are using and what kind of membership functions you employed?
Thank you.
Oh, both of them are working. Okay, super.
Thank you for your equation. It is. Thank you for your occasion. I have 4 membership. 4 membership. I have 4 membership is given by equation H.
What are your premise variables? I mean, the variables that you are using within the membership functions. Are they measurable? I mean, input, outputs? Or
No, now I have the input problem of 2 output problem. Donc, from input system.
X1 and X2, these are your
X2.
premise variables, but
State variable.
but they are not measurable.
Yes.
Okay. So how would you explain this? Because normally people are using the variables which can be measured directly, because it may cause some issues while implementing this in reality. You have to estimate them somehow, yes? Okay, with the observer.
Okay. Yes.
Okay.
Thank you.
Thank you. Are there any more? Sorry, you are.
Are there any other questions or discussions? Yeah, please.
The other question is why you use this finite frequency. Can you justify a bit better the use of this approach?
The finite frequency is divided in 3 parts: bass frequency, model frequency, and high frequency. Yes. Close. Thank you. Is this problem divided in this paper?
You need to approach. You need to approach close.
A detect of problem of the bass frequency.
But how do you determine this frequency? Because I didn't see any analysis of frequency. No. Where do you how do you decide these frequencies? How? In which manner do you decide?
Yes. 3 minutes.
Do you understand the question or no?
Yes.
How?
Can you?
No. You need to select a frequency range.
Frequency range, yes.
No? Because it's a finite frequency approach.
Yes.
So the question is, how do you determine this range in practice? The range of frequencies, eh?
The range of pressures?
No.
Of the fuel injection.
Your method is
Yes.
based on a finite range of frequencies.
On frequencies.
So my question is, how do you determine this range?
The fuel flow
No, not the rate.
output system.
Okay.
With the finite frequency is divided in 3 parts: bass frequency, middle frequency, and odd frequency. In this model proposed in this paper, the bass frequency, the fuel injection of output for model is infinite frequency domain.
Yes, no, I understand you, but the question is, how do you determine?
Yeah.
So your title is a finite frequency. You have
Yes.
3 frequency range.
Yes.
The question is how you decide which is the first one, which is the second one, which is the third one. Frequency.
Yeah.
That's the question. Do you know answer?
No problem.
Discussion afterwards, yeah. Any other questions? Can you go to the previous page, 20? Previous one, yeah. Okay. So you said the actuator fault is taken as the point G1, you know. What do you mean by that? What is actuator in a diesel engine? What is physically, what is actuator on a diesel engine? Do you know?
Wait, thank you for your equation. I have for the fourth F-type model, the modelization of the model nonlinear by the fuzzy system. We apply the fault between 0.25 and 0.6.
It's also, okay, let's maybe we have time. What is the actuator on the diesel engine? You have a diagram on diesel engine, right, in the beginning. And so first question is, what is the actuator you consider? What is physically, what is the actuator? The second is, what is the 0.5 mean actuator fault?
Thank you. The model.
Yes.
Yes.
Yeah.
Yes.
Yes. What is the actuator?
Well, we have controlling the VGT and EGR. Don't default the fault number 1 is, and the second fault for EGR.
Okay.
We apply two fault for exhaust gas recirculation.
So 0.5 means you skew it.
Yes.
So you skewed at the only quarter percent. Quarter,
Yes.
yeah. Okay.
Yes.
Okay. Any other questions? If not, we can move to the next one. Thank you.
Thank you.
Okay, thank you very much for your nice presentation. And we are proceeding to the second paper, which is entitled Evaluating Resilience Metrics in the Context of Safety Concepts, which will be given by Yin Yang.
Excuse me, going to begin by my PhD student. He could not come here because they did not give him the visa. So he's going to give us a presentation online.
Hi everyone, my name is Mohammed, and in today's presentation I'm going to discuss the resilience metrics in the power and control systems with the help of comparative analysis. First, in fact, all the reliability and optimization. Hi everyone, my name is Mohammed, and in today's presentation I'm going to discuss the resilience metrics in the power and control systems with the help of comparative analysis. First of all, I'm going to define the resilience concept and its definition. In the next step, I'm going to introduce the well-known developed resilience metrics up to now, and then we are going to compare these metrics to find out if they are capable enough to capture all of the resilience analysis feature and they are effective in defining the resilience level. The risk landscape of control and power systems have been reshaping based on two reasons. The first reason is that the number of extreme events or high-impact low-frequency events, including extreme weather events and human-made events, have been increasing. For example, this week an extreme flood happened in Germany. Or in the last 2 weeks, we had high winds and storms in Texas. So the frequency of these type of events have been increasing, and they are going to be considered as a new challenge for the power and control systems. As you can see, the contribution factor of these type of events in the power blackouts are considerable. The next reason is that nowadays we have more complex systems compared to the past, and enhancing the safety of these complex systems would be very challenging and expensive if we just rely on the well-known safety concepts like reliability and robustness, as through common approaches like redundancy. In fact, in the case of extreme events, with the unknown consequences, the complex systems with any degree of reliability can face the performance reduction and failures. So the safety design philosophy of the complex systems needs to fresh safety concept to consider this situation for the extreme events after the events and to reduce the performance degradation and expedite the recovery process. Based on the positive experience of other research studies and industries, the resilience, with the help of its unique features, can be considered as these new and innovative safety design concept. However, it's a new definition in the power and control system studies, and we don't have an universally accepted definition for resilience. However, up to now, we have these definitions in the area of power system. For example, IEEE technical report defined the resilience as the ability to withstand and reduce the magnitude and duration of disruptive events, which includes the capability to anticipate, absorb, adapt, and rapidly recover from such an event. Or, US National Association described the resilience in the terms of robustness and recovery features of the power system during and after disaster. The performance curve or resilience curve can help us to understand the concept of resilience better. As you can see in this diagram, the resilience covers the period from pre-disruption up to post-disruption. For clarity, two systems, the green one and red one, are compared in this temporal curve. Before the extreme event, here, in the case of common event, both systems are designed to endure common shocks and ensuring their reliability, without any performance reduction. However, in the case of severe events, in the T1, both systems strive to maintain the minimum critical performance level with the minimum degradation due to their robustness. By T2, both systems lose their robustness and face huge performance reduction. Here, between T2 and T3, we can see System A experience performance reduction but less than System B, with the help of resistance and absorption feature. Between T3 and T4, System A tries to prepare itself for the recovery and restoration program. For example, preparing some outage management programs and some equipment for the fast and efficient recovery process. At T4, System A begins to recover its performance, at least temporarily, since the full recovery process might take a long time. So temporarily restoration could help us to enhance the performance and provide the power for the at least critical loads. In contrast, as you can see in System B, or system with the traditional design concept, it starts the recovery and restoration process by delay after T4, and it requires a longer time for preparation. All the activity for the resilience system between T2 and T5, this period would be in vain if the system not be able to maintain the stability of the system and avoid the further performance reduction during the recovery and restoration process, as what happens for System B here. After starting the restoration, the traditional design concept might face further performance reduction. And the resilience system can maintain the stability with the help of some features like adaptivity and stability feature, which resilience system have. Based on this comparison, we can see how the performance of the resilience system and traditional design can be different in the case of a severe event. The resilience system tries to expedite the recovery and restoration process and reduce the performance reduction and preparation time. However, we have a longer preparation time and back into the normal operation for the traditional design, and also a huge performance reduction. Somehow we can say reliability is the base, fundamental concept, safety concept forming the base. Robustness builds upon the reliability and extend its scope by ensuring consistent performance under varying conditions and minor disruptions and disturbances. And however, resilience goes beyond these individual concepts. It not only encompasses reliability and robustness, but also extends the paradigm to effectively address the major disruptions and performance reductions, including both known and unknown consequences event with known and unknown consequences from before up to after, during and after the disruption period. In the next step, we are going to introduce some of the main resilience metrics developed up to now. I categorize all of these metrics into 4 categories, including optimization-based, trend-based, reliability-based, and performance-based. The optimization-based metrics usually just focus on optimizing the cost and time, and they are not able to give us important information and detailed information about the behavior of the system during and after the event. In fact, they are not able to follow the fluctuation of the performance of the system during the event and follow the recovery and restoration program and process, which is very important from resilience point of view. The trend-based metrics can, in contrast, follow the dynamic and fluctuation of the system after the event and during the event better. These metrics can define the speed of performance reduction, the magnitude of the damage, the duration of damage, and also a speed of the recovery process. But we should simplify the performance curve of the system after the event to trapezoid to use these metrics to define the slope of these lines, the performance reduction, and also the slope of recovery process to define the speed of the recovery process. The next category are reliability-based metrics, and as it is clear, they modify some of the reliability metrics to consider as a resilience metrics for resilience analysis. However, as we mentioned before, reliability just focuses on the area before the event, the period before the event, and avoids the failures. They cannot follow the fluctuation of performance and dynamic behavior of the system after the event and follows the speed of the recovery process. And these metrics usually calculates based on the expected values. The performance-based metrics are the last category, and similar to the reliability and optimization-based, they are static values. They cannot follow the dynamic behavior of the system, the recovery process after the event. The next section is comparative analysis. I have compared some of these metrics with the help of 4 conceptual case studies, as you can see in figure 2, which shows the performance of 4 conceptual power systems before, during, and after the event based on the time. The initial observation highlights that the results do not distinctly reveal the resilience level for each system. In fact, all the reliability and optimization-based metrics show equal results. It means that based on these results, all 4 systems have a similar resilience level. However, as we can see, the recovery time and performance reduction magnitude are different in each system. For example, we can see system B backs to the normal situation after 3 hours, however this time is longer for other systems. Or system D have a sharp performance reduction, which from mechanical point of view can damage the component harder. So reliability-based metrics cannot capture the essence and nature of the resilience based on its features very well. About trend-based metrics, also we can see it is unclear how we can calculate these metrics for some systems like system D and C, because we have to simplify the performance curve to the trapezoid, and each simplification format can lead to different results. Also for performance-based metrics, which they calculate based on the area under the curve, you can see systems A, C, and D have an equal value, which makes the comparison unclear. In fact, system A, as you can see, have a stable performance during the recovery process and during the event. However, system D have a lot of fluctuation, which makes the recovery process for the utilities harder and difficult from resilience point of view. So 2 main gap or downside of these 4 categories of metrics are as follows. First of all, these metrics cannot clearly distinguish the difference between resilience analysis and other safety concept analysis like reliability or robustness. The boundary of resilience analysis is not solidly defined, so we cannot clearly define the application of resilience in the power system design and safety evaluation. And the second gap or downside is that these metrics cannot follow and capture the main feature and characteristic of the resilience, which relies mostly on the recovery process and restoration process, the speed of the recovery, the dynamic behavior of the system after the event, the performance reduction or magnitude, and the preparation time, the damage time. So these are the gaps which should be considered in a way to find a way to develop standard and universally accepted resilience metrics. In summary, in this study, we emphasize on the importance of resilience analysis in the control and power systems. Moreover, we figure out that the current metrics are insufficient for accurate comparisons and do not fully capture all aspects of resilience analysis, which calls for more research to distinguish the resilience from similar concepts like reliability, and further research to reach and develop a standard and universally accepted metric for resilience evaluation. In the end, in this study, we use some conceptual case studies. Definitely, using realistic one can help us to reach more accurate conclusion. In the end, thanks for your attention and wish you a good and great time.
Okay, Mohammed made the presentation, and but I can ask, first of all, I can try to provide answers if you have any questions.
I wanted to say this, but...
Please. Oh, sorry, yeah, I steal the sender.
No problem. Okay, are there any questions or comments? If not, I will... Vicent, sorry.
Yeah, please.
I mean, the objective of these metrics is then to design the system to be more resilient, for example, or?
It's a way to measure the resilience. So in our FDI community, we said, how do we detect the fault? The fault tolerant control, we look at the configurations and so on to configure the controllers. But from overall point of view, we want to see the performance. How do we measure? You know, you have different ways to achieve the fault tolerance, but each one is different. How can you measure this? This is the concept of the resilience. It's not only just the detection, identification, but also the recovery part.
Okay.
So, but so far there's no universally acceptable definition. And the measure, not only definition, how do you calculate this? So we come up with some different way to evaluate measure of merit for to evaluate different techniques.
But the idea is to use this definition for designing a system to be resilient as well, or not?
We provide some guidance. But it's not, this has not been able to translate. That's what his PhD. Maybe in a couple of years, we'll be able to apply this to the design. So far, it's not yet.
Okay, thank you.
We identify the drawbacks of existing the definitions, existing measures. Then we say, well, what we propose, it's more complete than the existing one.
Thank you. Are there any more questions or comments? If not, then I will ask one.
Yeah, please.
If there are several metrics, it goes without saying that one of them will be better, second will be worse. And the question is there a chance to combine them somehow, for example, using the Pareto front to give some, how to say, more trustful response?
Yeah, definitely. It's not only to combine them. We got to understand what is the sensitivity of each measure. For example, he gave this A, B, C, D's, 4 systems. They have the same, if you measure the reliabilities, they're almost the same. But each one is different. Some fault is very large, but recover very fast. Some fault is very small, but take a long time to recover. So how do we measure that? The next step is how do you translate design the control, design the detection, so that we can minimize these disruptions to the performance.
Thank you. Thank you very much. We still have got 3 minutes. I don't want to play ping pong with you. I will ask you a question. No. Okay. So let us proceed to the next paper. You will introduce this next paper, yeah?
Okay. I will introduce the next paper, but next paper is again, it is, I think, by...
Good evening, everyone. Thank you for... Good evening.
So the next paper is consensus-based control for multi-agent system with a TS model and parametric uncertainty. It's given by recording.
Good evening, everyone. Thank you for your presence. I am Sherigi Ayoub, second-year PhD student from IBISC Laboratory and the Doctoral School of Paris-Saclay.
Can we make it louder?
I will present you. Good evening, everyone. Thank you for your presence. I am Sherigi Ayoub, second-year PhD student from IBISC Laboratory and the Good evening, everyone. Thank you for your presence. I am Sherigi Ayoub, second-year PhD student from IBISC Laboratory and the Doctoral School of Paris-Saclay. I will present you my work done on the accepted paper titled Consensus-Based Control for Multi-Agent System. Good evening, everyone. Thank you for your presence. I am Sherigi Ayoub, second-year PhD student from IBISC Laboratory and the Doctoral School of Paris-Saclay. I will present you my work done on the accepted paper titled Consensus-Based Control for Multi-Agent System with TS model under parametric uncertainties. The authors of this paper are me, Dr. Nashidi Laborel, and Professor Shedley. The presentation plan will be as follows, starting with the research motivation, then introducing some notions about graph theory and TS modeling for agent system as we can call mass. Then followed by the consensus strategy for multi-agent system without and with uncertainties. Simulation and the result will be shown next, and finally a conclusion. Mainly the robotic system was developed previously to work autonomously and individually. Then, by observing some natural behavior and phenomena from animals and insects, research and engineer worked on developing technologies that allows to connect this robotic system and create a network between them, calling them all multi-agent system. The main advantage using this technology is that this system is easily adaptable to different tasks, and it is flexible and learn from its environment. The robotic system is robust and remain operational despite individual agent failure. It can execute simultaneous tasks and reduce compilation time. The agents perform specialized tasks effectively and can be reconfigured easily. It enables complex interaction and reduce the cost effectively. It also ensures reliability and efficiency for large area coverage and monitoring. As all system faces challenges, the system has nonlinearity and uncertainties and disturbance that act on it, including the complex nonlinear control design that could not exist at all, the computing process complexity, and so on. For this reason, the choice of TS model approach has been proposed to simplify the system representation, keeping its nonlinearity, and also simplifies the numerical implementation. Moving now to some preliminary starting with graph theory notation that are used in math. We have a connected graph between nodes that we call agents, and the edges that connect between these agents that flows information between them. So, mathematically speaking, this graph can be represented by a matrix called Laplacian. It is calculated using the adjacency matrix, representing the number of connections for each agent, and the degree matrix representing the number of output or input connection agent. And this last matrix is a diagonal matrix. The graph can be represented with a centralized or distributed topology, and the communication can be directed or undirected. That can be flow in both ways. The graph can be strongly or weakly connected. And in our study, the graph is distributed, directed, and weakly connected. Now, since the graph theory is presented, the TS model, fuzzy model notion for multi-agent system is introduced here. Supposing that we have an agent I represented by a nonlinear equation, where its dynamic is dependent on its own states and input controller. The TS model approach can be proceeded or processed in 3 different methods. Firstly, we find the method of identification where the real system output are approximated by some linear model depending on their input. We have also the linearization method. Here the system is linearized around some known operating states with linear behavior. And finally, we have the polytopic approach where the state of the system are bounded with maximum and minimum. Those boundaries are linked, creating a polytop to represent the state space of the nonlinear system. As a result, the TS fuzzy model for an agent I is represented as shown here, where we can see some additional variables like the state decision variable Z and the fuzzy membership function mu. Since the paper is treating the parametric uncertainties, additional notation considering the uncertainty on the dynamic matrix A on each subsystem of each agent. Noting also that all the agents in this multi-agent system in the studied multi-agent system are homogeneous. The global multi-agent system dynamic is as follows, which brings together all the dynamics of all the agents. As the system should be controlled, the consensus control strategy is proposed in this paper could be introduced as the following idea, where we have a system with an initial condition, state condition. Then by applying the consensus strategy, the system dynamic progresses over time to reach this consensus between the agents. The controller equation is represented here, where it corresponds to a modified state feedback parallel distributed compensation control called PDC. With Kn, our matrices representing the controller gains for the N subsystem. We can write the controller formula in a matrix manner to enable stability analysis by follow. Now the controller is represented. The stability analysis could be done by using the quadratic form of Lyapunov candidate function, as shown here, as an energy equation of the states, where P is symmetric positive definite matrix that should be found to verify the stability of the system. Here some assumptions and notions concerning the graph representation for multi-agent system, where we can change the form of the Laplacian of a D-graph into a Laplacian of a non-directed graph and then finding this matrix, we should search for a matrix R that allows a model transformation of this new Laplacian matrix that allows at the end putting all the eigenvalues of this Laplacian matrix in a diagonal matrix. Firstly, the stability is analyzed with no uncertainties on the system. The following lemma from the reference below describes the stability conditions as the following LMIs. Then the parametric uncertainties is added following the structured way, where matrix D and E are known matrix, and F is a variable, unknown, and bounded matrix. Then the final representation of the global control system with the uncertainties is shown as follows. Stability study leads to this theorem, given the following LMI's condition to satisfy stability of the uncertain multi-agent system, and also computing the maximum boundary of each subsystem for each agent. To show the efficiency of this control strategy, the following example from reference below is implemented, describing the dynamic of 3 solid objects and their communication topology is shown in the figure behind. The TS model is derived around 4 operating points, and the membership functions are set as represented in the figure. Some numerical information are needed here to initialize simulation, as the matrix Laplacian matrix, the initial condition, and the choice of parametric uncertainties. After running the simulation on MATLAB using SDP-3 solver on YALMIP to optimize the LMI conditions shown in the theorem, the computed controller gain and the boundary of the uncertainties are shown as follow, where we have four gain matrices for the controller and four boundaries for each sub-dynamic system shown and defined in the theorem equal to 0.5. Finally, we can conclude that the consensus-based state feedback PDC controller for uncertain TS fuzzy multi-agent system is done properly by verifying the stability using a quadratic Lyapunov function, setting up LMI's condition to compute the controller gains, then showing the good performance of this algorithm on simulation. For perspective of this work, additional uncertainties could be proposed on the input matrix B with unknown inputs, and changing the quadratic form of this of the Lyapunov function for the stability analysis to a fuzzy function to relax the stability analysis. So thank you for your attendance.
Any discussions on this paper? We cannot ask questions, but any discussions, any comments? Okay. Not, we can move to the next one. But before that, I will ask is the people present for the last paper of this session here. So obviously we did not. So you probably the last paper.
Yeah. So I've got a pleasure to introduce the author of the last paper in this session. As we hear, there is now fifth author present so far. And the title of this paper is Switching LPV Approach for Analysis and Control of TCP-based Cyber Physical Systems under Denial of Service Attack. And the paper will be given by Vicens Puig.
Okay, so thank you for the introduction. We start? Oh. Almost the last. Okay, so this is a work with my student who couldn't come because he's in Iran, and Marzin that is here as co-author. So the outline of the presentation is the following. First, I will motivate a bit the problem. Then I will present the problem statement, and then I will derive some methods for analyzing the stability and the controller design. Finally, a case study that is used in the literature will be used to compare the proposed approach with the current solution in the literature. And finally, the conclusions. So let me start. The paper is dealing with a problem that, in fact, it's presented in the plenary this afternoon by Ping Thang. Is the problem of the systems that now we have that are integrating communications, control, and computers. No? So altogether, as you know, these receive the name of the cyber physical systems. Okay? The point is that this integration provides a lot of benefits because of the interconnectivity, the flexibility, etc. But also this produces or facilitates the cyber attacks. Cyber attacks in the sense of cyber physical attacks, because in our community we are not concerned about computer only attacks. So for dealing with the security, not the safety, it's also the discussion, there is a growing area of research where this aspect is addressed. In particular, also as Ping Thang commented during the talk, there are many attacks. There are many types of attacks. In fact, she listed the most known. And in particular, in fact, the one that commented the first, because maybe it's the most known, is the denial of service. This is very famous because it's the usual one that the hackers use. For example, for a web server, making it down. And basically, this attack consists in disrupting the system availability by overwhelming it, sending a high volume of data or requests. That this causes the packet drops or delay in the transmission. So this is the problem that we are going to deal in this talk today in this paper. So, in particular, the paper investigates the problem of analyzing the stability of a control system when such kind of attacks appear, and also design a controller that is able to deal with. Also taking into account that additionally to the attacks in the networked systems, this is classically known, there are delays. Delays that usually are not constant, are varying, because as you know, when you connect to the internet, sometimes the network goes fast, some other times go slow. Another novelty of the paper that was considered is to consider in the design these delays, and these delays taking into account the level of congestion of the network. So in the literature, there has been a lot of work, especially from the people from communication field, to characterize the congestion in the case that the protocol is the classical one used in the internet communications, that is the TCP. So for the TCP communication systems that are the most usual in the internet, there is a model that takes into account how the delay varies according to the congestion. So we have some relation between delay and congestion. So this is the model that we will include in the analysis. When considering all these facts all together, and we create an augmented system, then the system that, even though at the beginning we consider that the plan in this particular paper was linear, because of this delay vary with the operating point, with the congestion, and taking into account the model of the network that is non-linear, we arrive to a non-linear time-varying system, okay, regarding the delay. That in this paper it's represented as a linear parameter varying model. But there is another factor that here is considered, is the fact that since this denial of service produces a packet loss in a random manner, we need to characterize this in a probabilistic way. So the paper suggests the combination of this time-varying delay LPV system with the probabilistic representation through a Markovian jump system. So quite complex family of models in this case. So finally, as I said in the outline of my introduction, we select a case study that is quite known in the network control systems to illustrate how the analysis that the paper proposes improve the results that are already existing in the literature of networked control systems, not in particular considering attacks, but the delays. Okay, so let's move to the problem statement in this paper. In this case, as I said, we could use a nonlinear model because at the end we arrive to an LPV representation of our system, but as it was originally formulated in the paper, we consider that we have the plan that is connected through the network, same setup that Ping Thang in the plenary, and the plan is assumed to be linear, but could be nonlinear, no problem. At the end, it doesn't matter a lot if we represent in an LPV manner. But anyway, at the beginning, we consider the plan as a linear representation, and the control law, it's defined as, in many, let's say, networked systems, as an state feedback with delay. And this delay is typically varying, as I said, according to congestion. So additionally, this is the setup. So the controller sends the control actions once the state is measured with some varying delay, is sent through the network to the plan, but in the middle, as also in this talk, some attacker, it's trying to interrupt the communication between the controller and the plan by injection of this denial of service problem. So as I said in the introduction, also the paper introduced another novelty regarding the analysis. As I said, the delay is varying. In reality, the delay takes into account the delay in the two sides, the transmission between the controller to the plan and the plan to the controller. There are two delays here. So these two delays are the total delay of the transmission. And in reality, these delays are unknown, but depend on the congestion. But there is, let's say, a model, as I said in the literature of communications, that tries to characterize how the delay varies according to congestion. So this is a bit the novelty of the paper, including this model of the delay in function of the congestion. So at the end, in this model, I forgot to say that you can see here, that there are some nonlinear relations. So when considering the congestion, how affects the delay, the model becomes nonlinear. And considering the total behavior of the system, the plan plus the network, we have an augmented system that is represented in an LPV manner. The details of how the transformation is done are detailed in the paper, but we use the standard manner that is called the nonlinear embedding of the nonlinearities. Nothing new here. So at the end, the model of this cyber-physical system, it's expressed in an LPV system with delay. Here we can see the delay due to these communications between the plan and the controller through the network. So now let's include the denial of service attacks. As I said, up to this point is a classical network control problem. There are already results in the literature regarding this problem, but here we add another novelty, that is that someone, as I commented at the beginning, is injecting the denial of service that cancels the connection between the controller and the plan. So we can imagine that this can be mathematically modeled as a switching signal that is aleatory between 0 and 1. 0 means that the connection is lost, 1 that is not lost. But this loss of connection is random. We cannot anticipate. Or at least here is assumed that we don't know, because it's the attacker that introduces this. So 0, as I said, indicates that the plan receives the data with delay, of course. As I said at the beginning, because we are in a delayed network. And if it is 1, then it means that the packet is lost. So at the end, the controller, depending on the state of this switching variable, close the loop or is open loop at the end, is what happens. So altogether, at the end, it's modeled as an LPV system that additionally to consider the, let's say, varying part that includes the nonlinearity, this rho, as classically in the LPV systems, include another variable that is random, that is this, let's say, variable that takes into account if the packet is dropped or not. And this leads to a continuous Markov jump system, that there is a matrix of transitions that should be characterized. This is in the paper in detail. I will not enter into all the detail because it's a bit long. So the interesting thing is that in these Markovian jump systems, it is defined what is the stochastic stable property that guarantees that in mean value, the stability will be guaranteed. And considering the mean value stability concept, then you can generalize the stability to this family of systems in a similar way that we do with, let's say, deterministic systems. That's the spirit. So, but formulating, of course, in the vertices of the LPV and modes of the switched system. So the first result that is in the paper is regarding the stability. So in this case, we are concerned about what happens in the system when the controller is already designed. We don't know how. We have a controller, and we want to verify if, because of the existence of these varying delays plus the denial of service, we can guarantee the stability or not. So this is what this result provides. Basically says that to guarantee the stochastical stability of this time-delayed Markovian system, we need to satisfy this condition. It's an analysis result. The proof is not presented here because of the length of the, let's say, proof. You can see in the paper. It's classical proof in delayed systems and is based on the extension of the Lyapunov systems to the time-delayed systems that is done through the Lyapunov-Kryakowski functional. It's a standard manner for the time-delay systems. So once we have the first result that the paper presents that allows to do the analysis, it's, as always, when we have the LMI that allows the analysis, we can inject in the LMI through the congruence transformation the controller, and we can produce the LMI for design. And this is what it's done in the next. So using the previous LMI that is only for analysis, in the previous LMI we assume that the controller is already designed. Now we reformulate the problem saying that the controller is not known, need to be designed. And by including this controller that, as I explained at the beginning, has this structure injected in the system, but also including the, let's say, the stochastic part, not only the deterministic part, we can reformulate the previous, let's say, result using the typical congruence transformation that leads to the LMI for design. So once the main results for addressing the problem I presented at the beginning have been introduced, of course, here is only stability conditions. We can add, of course, more conditions regarding performance. Here is just to illustrate the approach. Let's move to the case study. The case study is a standard one in the literature of networked control systems. Is a very simplified model for an unmanned grounded vehicle, an autonomous vehicle, only considering the speed and the position that leads to this dynamic model. It's very simplified. It's not like the bicycle model or other more complex models that exist for autonomous vehicles. It is a very simplified model. So in the first experiments, as I said, we assume that the controller is already designed. In fact, in the reference where this example is proposed as a case study, the controller is given. And basically what we do is we simulate, well, first we will test everything in simulation because we don't have the real facility for doing this. And also including the model of the network that, as I said, is one of the novelties of the parameter. We use a simulator that is able to emulate the behavior of the network considering all these parameters here. I will not read all of them, but are needed for parameterizing the TCP model of the network. So basically, regarding the stability analysis, in the first moment without attacks, later we'll introduce attacks, show that the method is able to determine the maximum allowed delay in the communication, taking into account the capacity of the connection and the length of the buffer. These are the most critical parameters in the communication. So in particular, using the theorem that I presented, when there is no denial of service, we arrive to some results. But to know if these results are relevant, what we have done is what is presented here. We compare with other similar approaches in the literature that deal with the same problem, but without considering the TCP model I was presenting you. So here we want to show that using the approach, we are able to tolerate more delay than other methods, showing that the results that we produce are significant. Also, we analyze how this acceptable delay depends on the denial of, say, of attack rate. So depending on the frequency that the attacker injects the packet drop. So here in this plot, we can see how this number was when no attacks. This is a number I was showing. But when you start incrementing the rate of attack, we see that this level decreases. But with the method, we are able to know until which rate we can accept. This is only the analysis. The second part is to show that with a method, for a particular rate of, let's say, denial of service, we can guarantee the stability by designing the appropriate controller. So let me conclude. In this paper, what we have done is to present a problem that is nowadays of interest, that is the problem of analyzing the cyber-physical systems when one particular type of attack, one of the most known, is the denial of service occurs. The paper also introduced not only a method for analyzing this problem, but also include an improvement with respect to previous results in the literature, is that the delay, that is one of the main factors in networked control systems, can be included in the model by taking into account the TCP communication dynamics. All the analysis leads to formulate the problem, as we have seen during the presentation, to a model that includes the dynamic of the plant plus the dynamic of the network, leading to a switched LPV system with mark jump transitions that are related to the denial of service. The paper also has derived two results, one regarding the analysis of stability given the controller, and the extension when the conditions are used for design, to design a controller that by design takes into account this fact. And finally, the paper concludes introducing a very well-studied example in the network control literature to see the improvement that this approach provides compared to existing results in the literature. And that's all. Thank you.
Okay, thank you very much for a very nice presentation. Are there any comments or questions? If not, then
maybe I'll ask a question.
Yeah, you will.
This is very interesting presentation. Just one simple question on page 20, the table you showed. This is theorem 1. You have two lines. Yeah, the first one, the second one. What's the difference?
There is a mistake. No, some number is wrong. I don't remember, but maybe some number is different for different.
Yeah, it has to be different. Okay, fault detection. This is fault detection. No, this is a trivial.
I think it was written before running.
Yeah.
Here, the number that is wrong is that in one case the buffer is
Okay.
and the other is 200.
Okay.
But in the table is incorrectly written.
So my question is, my question, I'm sitting in front, so my question is the simple system that the example you gave, that's just, mass spring, it's very simple, with acceleration. When you say stability, for this simple system, what do you mean by stability? It should always be stable, right?
Well, because of the delay, no. Because of the delay can be unstable, no? The delay and the denial of service, no?
Yeah.
But in any case, as I said,
is the open loop stable or not? Open loop stable or not?
I don't think so. No, I have to check. I don't remember now. But why we select this example, I told you.
Okay, it's
because in the literature is widely used.
Okay.
And to have a reference if our numbers are competitive, but yes, it's a good question, very good question.
Okay.
In any case, the method here is not presenting this extension. I mean, at the end is what I explained at the beginning.
Yeah.
When you include the model of the network, it's presented here, this already includes some nonlinearity that forces that even though the plan, as I said at the beginning, is linear, could be extended to the LPV because you are already in the LPV. We could use this for a more complex vehicle.
During the denial of service, basically system become open loop.
Exactly.
Thank you very much. Thank you. So we come to the last presentation, but we have to load this on, okay? So just give me a second. safe process? Is that it's this one, right? Any. Maybe I should put it on so that you can use the pointer. Just a minute. Yeah, just a minute. I think I should put this. Close yours. Okay, so next presentation is does it work? Does the flip work? Okay, yeah, good. Is the last paper of the session. It's called optimal fault-tolerant control strategy for continuous fermentative bioprocess for biomass production. Okay, this is quite a. Anyway, you can read that. So please go ahead.
Thank you. Water is an essential resource for the existence of life on the planet. Then efficient wastewater treatment and energy recovery are imperative. Good afternoon, everyone. My name is Joel. I work at the University of Guadalajara, Mexico, and today I'm going to give a short presentation on fault-tolerant control applied to bioreactors producing biogas. The fermentation system is a nonlinear multi-step degradation process where complex substrates are progressively degraded into soluble ones by facultative bacteria. This process is economically viable due to high rates of biogas production, recovery of high added value byproducts, and low cost of renewable sources. Due to the nonlinear nature of the process, the efficiency could be affected by physicochemical variables such as pH, metabolic pathways, and associated microbiome. Then, optimal operation is relevant for the continuous activity of biogas producing bacteria. Feeding actuator failure is one of the most common failures or faults in fermentation reactors due to mechanical components degradation or saturation. Then the opportune detection of pump faults can be helped to diminish maintenance and operation costs, prevent performance degradation, and damage to machinery or human life. In order to address this problem, a fault-tolerant control strategy for nonlinear systems based on artificial neural networks and inverse optimal control law for trajectory tracking is proposed. The neural network estimates the process states and the output. The output is the volumetric flow rate of biogas, and the optimal control is used to stabilize the system and improve its performance in presence of actuator failures. The objective is to lead the system to a safe operation and to minimize the loss of productivity. A mathematical model, not nonlinear model, is used to describe the anaerobic digestion process with two continuous operating reactors for simultaneous hydrogen and methane production. Reactors operate at different working volume, where the outflow of the first reactor is the feed of the second one, and the produced outflow is removed from the top of each reactor. Equation 1 describes the dynamic states of the hydrogen reactor, where D1 is the input dilution rate, Psi variable is the states as substrates and biomass, Y parameter is, represents stoichiometric parameters, Rho is the biomass specific growth rate, and F is the input mass flow rate. Equation 2 describes the volumetric flow rate of biogas, and equation 3 and 4 describes the dynamic states of the methane reactor. Then, a autoregressive neural network structure is used to identify dynamic states in the reactors, and it is described by equation 5 to 8. This structure allows the flow of information in a forward and backward direction, improving its dynamic behavior and also improving its learning capabilities and performance. This neural network is trained with an extended Kalman filter algorithm to update weighting matrices. And additive control is proposed based on inverse optimal control law for trajectory tracking. And the system is described by equation 9 and 10. Optimal control is based on models affine to the input, and the control input is composed by stabilizing components and the additive control to compensate the fault effect. This control law satisfies the passivity inequality equation 15 by proposing a Lyapunov storage energy function, and also minimizes the cost function 16. On the other hand, a decision logic criterion proposed by Nemati is used to identify the faulty presence. The criterion is based on the output estimation error as R subscript K, and the L2 norm is used as evaluation metric. JBD is the supremum norm of gamma, and gamma is defined as the uncertainties and disturbances of the system. For the fault-free case, the variable Rk is the residual signal, is less than or equal to supremum norm. For the case of major actuator failures, an actuator with blocking or complete loss with an actuator redundancy is considered. The control system is described by equation 20, where D subscript J is a constant failure, and it is equal to the blocking value corresponding to the Jth actuator. However, if the actuator is lost, D is null. Then the objective is to find a control law that satisfies the physical constraints and lead the damage system to an optimal operation. Then a threshold for the admissible lowest quality ADA, where the system can continue to operate with degraded performance, is proposed by NORA. This quality indicator is equal to the permissible maximal output error and the control effort, and L and R are weighting matrices. The decision logic is proposed is described by equation 23. For the case when eta is larger than cost function, new reference trajectories for the whole system are proposed in order to lead the damaged system to an operating order rather than stopping it. Now, let's move on to the simulation results. For the first case, the additive control is tested under two degradation failures, as described in table 1. When failure F1 appears in actuator D1 at 500 hours, the control effort decreases and the trajectory tracking is affected for the hydrogen production. After that, failure F2 appears on actuator D2, affecting the operational equilibrium of the methane reactor and also affecting its trajectory tracking. Table 2 describes the parameter, the residual signal, in order to detect fault presence. By applying the additive control to compensate faults in actuators, reference trajectories are reached and the optimal control of both reactors are ensured. The effectiveness of this strategy resides in the accurate fault estimation and the optimal control law. For the second case, an actuator blocked is considered. Actuator D1 is blocked at its current value in steady state at 1,000 hours, and the tracking error for hydrogen increases. In order to address this problem, reference trajectory for methane reactor is changed to a lower operating order, and this new reference trajectory is selected based on the physical constraints and the quality indicator. As can be seen, the reference trajectory allows the methane trajectory tracking by decreasing control effort in actuator D2, avoiding emptying of the hydrogen reactor and a critical operation of the whole system. By monitoring quality indicator, new reference trajectories can be proposed in order to drive the system to a optimal operation with respect to desirable performances, degrees of priority. To summarize, the fault-tolerant control strategy is efficient to stabilize the biofuels production along the desired trajectories in presence of actuator faults so that the passivation of the entire plant is preserved. This project is supported by CONACYT, and it is developed in collaboration with Center for Research of Jalisco, Mexico. Here's some reference of the project. Thank you for your attention.
Any questions? Comments?
Sí, sí.
The constraints regarding the here, where you how do you consider in your approach explicitly the constraints?
Constraints?
Yes, because here you introduce some constraints in the state, the control. In your method, when you do the design, there is I haven't seen the way you include these constraints in the design.
Constraints are physical constraints.
Yes, yes, I know. But I mean, you can guarantee that the controller satisfies these constraints?
Yes.
How?
How?
How does your algorithm manage with the constraints?
Okay. Reference trajectories are selected based in an input-output analysis for maximal production of biogas based on equilibrium points, based on maximal points for biogas production. Then exists a number of desirable trajectories for optimal operation, local operation or global operation. Then these reference trajectories are selected based in this criterion.
No, I understand this, but there is no way in your approach to explicitly guarantee that your variables will be within these ranges, no? Do you follow me? I mean, in the design process of your controller, there is no way that you explicitly establish that the control action, for example, is in that range, no? I mean, for example, in the plot, no? In the plot you show that is 0, 0, 0, 4. Can you guarantee that the control signal never exceeds 0, 0, 4? How do you guarantee this?
It's not zero. Zero is positive. It's a signal. It's a positive signal.
But for example, if I understood well the plot, if maybe it's misunderstanding, but the control signal should be within 0.1, 0.04.
Yes.
And here you arrive to 0.04 in the peak.
Yeah.
How this is guaranteed that you never exceed 0.04? This is my question. How do you guarantee that the action never exceeds?
It is based on the reference trajectories.
But this is in the steady state. But in the transient, how do you guarantee?
Yes, the operation is based on the reference trajectory.
I understand your point, but
yeah.
What I'm trying to say is that in the design process that you present us, there is no way where you explicitly.
Okay.
You understand? For example, in MPC,
it's implicit. It's implicit.
Implicit, but in which point? But anyway.
What happens when you do the calculation? The control signal is 0.05. Calculate 0.05. What are you going to do? Are you going to cap it to 0.04 arbitrarily?
Because the reference is selected based.
If you calculate, this goes to up here.
Yeah.
What are you going to do? That's the question.
There is no. This is not bounded.
It's not bonded, so it's not guaranteed. There's no guarantee.
It's not bonded.
Yeah, that's the answer. Yeah.
But the reference trajectory.
Yeah.
The reference trajectory.
Yeah. There's no bond. So yeah.
Is proposed for the control is in this.
No, we are not examining you. We're just asking you some questions. Any other questions, comments? Yes, please.
Thank you for your presentation. My question is about how do you ensure stability under the influence of faults? So when the faults have occurred, how do you ensure that the system still remains stable?
Do you refer to stability?
Yeah.
The stability is obtained with the Lyapunov storage function. The Lyapunov storage function guarantees that the dynamic states are asymptotic stabilizing along the desired trajectory. But the control is an stabilizing control along the desired trajectory based on Lyapunov function.
But also under the influence of faults, can we still ensure that it is stable? it'll be
Excuse
stable.
me, could you repeat?
When the faults have occurred, can we still ensure that it will remain stable until the fault?
This is the purpose. Stabilize the system in presence of disturbances.
Okay, yeah, thanks.
Yeah.
So I have a simple question. Is this a simulation or is this experiment?
It's simulation.
But then you present, in the beginning, you present you have apparatus, system.
Because I have reactors, and the future work is to apply this strategy in real time.
Because this is 3 months. This period is 12,000 hours.
It's a
This is a very long process.
yeah, the process is performed in 1 or 2 months. It's a long process. Yeah.
Any other questions? Okay. If not, can I just close the session? And so thank you very much. So thanks all the speakers and the audience. And this is the last session, last paper of the conference. And I'm very happy that you all stick around. And I'm officially close the session. And we have a closing ceremony in a few minutes in the main theater. So I think we should all go there to celebrate. Yeah. Thank you. Thank you.